when the night wraps around you like a soft blanket and the noise of the day fades into a gentle hush, your mind begins to wander. Where does it go when it's quiet? Maybe far beyond Earth, into the calm and endless dark. Tonight we'll tell you space facts to fall asleep to. Slow stories from the universe, spoken gently to help your thoughts settle and your breathing slow. Each one is a step further from the day, deeper into space, and closer to sleep. Close your eyes, breathe in, and let's begin. The forgotten Soviet probe, Cosmos 482, returns after 53 years. In 1972, during the height of the space race, the Soviet Union launched a spacecraft called Cosmos 482. Officially, it was just another routine satellite. Unofficially, it was meant to land on Venus. But something went wrong. Shortly after launch, the spacecraft failed to escape Earth's gravity. Instead of soaring toward Venus, it got trapped in orbit and forgotten. For more than 50 years, Cosmos 482 has been circling silently, becoming little more than space debris. No transmissions, no noise, just a shell of metal drifting high above us, like a message lost in time. And then, in 2025, something unexpected happened. Observers tracking near-Earth objects noticed a new bright trail in the sky. It turned out to be part of Cosmos 482, breaking through Earth's atmosphere after half a century. A capsule from the probe had survived re-entry and landed in New Zealand, scorched but intact. Think about that. A machine launched by hands half a century ago. Returning home, it carried no data, no mission logs, no samples from Venus, just silence and history. Now, scientists are studying the remains. Its titanium shell, built to endure the brutal atmosphere of Venus, had instead outlived generations of people back on Earth, a monument to forgotten ambition, falling gently back into our world. As you drift deeper into sleep, imagine it, a small, ancient probe returning from nowhere, quiet, charred, and full of stories we never heard. Why the moon looks bigger at the horizon, the lunar illusion. You've seen it before, rising slowly above rooftops or glowing behind trees. The moon, hanging low in the sky, looks massive, almost too big. A perfect silver coin, close enough to touch. But here's the strange part. The moon isn't actually any closer. It's not larger either. This effect is just a trick of the mind. It's called the lunar illusion. When the moon is near the horizon, your brain compares it to things you can see. Buildings, hills, trees. It feels close, grounded, part of your world. Your mind stretches it, gives it weight, scale, presence. But when it rises higher into the sky, away from reference points, it suddenly seems smaller, more distant, like a glowing marble against an empty backdrop. Some scientists believe it's not just perspective. It might be the way our eyes and brain process angles. Or maybe it's emotional. The moon low in the sky feels more intimate, more poetic, more real. For thousands of years, people have watched that same illusion. Poets wrote about it. Sailors steered by it. Children dreamed under it. And now, so do you. Tonight, as you drift into sleep, picture the moon rising slowly over a dark, quiet landscape. It hasn't grown, but it feels big, not just to the eye, but to the heart. And that feeling somehow is real. How plants might grow in space, what we've already tried. Imagine a tiny green leaf opening slowly, not under blue skies, but inside a quiet space station orbiting hundreds of kilometers above Earth. For decades, scientists have been trying to answer a simple question. Can life take root in space? The answer, quietly, gently, is yes. But it wasn't easy. Back in the 1980s, the Soviets grew the first flower in orbit, a small Arabidopsis blooming aboard the Salyut 7 station. It stretched toward fluorescent light, its roots floating in air, its leaves trembling in microgravity. Since then, astronauts have experimented with wheat, lettuce, mustard, radishes, and even chili peppers. Without gravity, water behaves strangely. It clings to roots in unpredictable ways. Stems don't know which way is up. Light has to be carefully placed to guide their growth. But still, the plants adapt. Some curl, some float, some even thrive. In 2015, aboard the International Space Station, astronauts tasted space-grown lettuce for the first time. Freshly harvested, bright red, and surprisingly crisp. It was more than a snack. It was a symbol, a promise that one day, far from Earth, we might build gardens on the moon or on Mars. Plants are more than food. They clean the air, stabilize the mood, and give us something familiar, a little patch of Earth when we are impossibly far from home. So tonight, as you close your eyes, picture a single green sprout drifting in weightlessness, silent, determined, and growing leaf by leaf into the future. What NASA's New Mars rover can actually do. Somewhere on the surface of Mars, a small machine is moving slowly across red dust, one careful wheel at a time. It's quiet there. The wind is soft. The sky is pinkish gray. And the rover is thinking. NASA's latest rover isn't just a camera on wheels. It's a laboratory, an explorer, a scout, and a survivor, all in one. It can navigate rough terrain on its own, choosing where to drive without waiting for instructions from Earth. It uses artificial intelligence to avoid hazards, to scan rocks, and to decide which ones might hold the secrets of ancient life. Its robotic arm can drill into stone and store samples for future missions, small tubes of Martian soil and dust, waiting patiently to be brought back to Earth one day. Maybe in 10 years, maybe more. The rover has microphones. It can hear the whisper of Martian wind, something no human has ever done. It has lasers too, not for weapons, but for science. They zap rocks and listen to the sound the vapor makes, revealing their composition. It carries a helicopter too, a tiny craft named Ingenuity. It flies in thin air where no aircraft has flown before, taking photos from above, scouting paths ahead. It's alone, but it's busy. Far from home, this machine is laying the groundwork for future astronauts, for habitats, for greenhouses, for footprints. It's not just exploring, it's preparing. As you fall asleep tonight, imagine the silence of Mars, broken only by the crunch of wheels, the hum of instruments, and the quiet, steady heartbeat of a rover doing its job, tireless, patient, and always looking forward. What would it feel like to stand on Mars? Atmosphere, radiation, and cold. Close your eyes and imagine this. You're standing on Mars. The ground beneath your boots is dusty and red, a fine, rust-colored powder that stretches for miles. The air is thin, far too thin to breathe. Your visor fogs slightly as you exhale, and everything is silent except for the faint hum of your life support system. The sky above you is not black, but tinted orange and pale pink, almost like a sunset that never ends. The sun is smaller here, colder, more distant, and the wind is soft but sharp, rushing across the barren landscape at dozens of kilometers an hour, carrying grains of sand that sting, if not for your suit. The temperature, bitter cold, far below freezing even in daylight, and at night it drops even more, enough to freeze steel. You wouldn't last long without protection. And then there's the radiation. Mars has no magnetic field to shield you, no thick atmosphere like Earth's. Every second, particles from the sun and the galaxy rain down. Not enough to burn your skin, but enough to matter. Enough that one day, if we live here, we'll need to build shelters underground or beneath domes. Still, there's something hauntingly beautiful about it. No sounds, no cities, no movement, just stillness. Just the crunch of your steps. Just the feeling that you're standing on another world. A world no human has ever truly touched with bare hands. And above you, hanging quietly in the Martian sky, is a tiny blue dot. Home. As you drift toward sleep, imagine that moment, standing on a red horizon, feeling the silence of an alien world, and looking back at Earth, fragile, distant, and glowing. The first moon landing. What really happened in 1969? It was July 20th, 1969. Somewhere, televisions were flickering in dark living rooms. Radios whispered static-filled reports, and over 300,000 kilometers away, a fragile spacecraft was descending toward a silent, powdery world. Inside it were two astronauts, Neil Armstrong and Buzz Aldrin, holding their breath as they dropped toward the moon. What many people don't know is that the landing almost didn't happen. As the lunar module approached the surface, alarms started going off. 1202, 1201, cryptic codes no one had expected. Back in Houston, engineers scrambled to interpret them. Meanwhile, Armstrong looked out the window and saw that the autopilot was guiding them toward a field of boulders. Not safe. He switched to manual. With less than 30 seconds of fuel left, Armstrong flew the module across the surface, searching for a flat patch of ground. It was quiet, tense, and impossibly delicate. And then, dust kicked up. A shadow formed, and they were down. "Houston," came the words. "Tranquility Base here. The Eagle has landed." Hours later, Armstrong stepped onto the surface and said the words you know. That's one small step for man, one giant leap for mankind. But what the world didn't hear was the sound of his breath, the way the dust clung to his boots, the silence of a world where no sound could travel, only radio signals, only heartbeats. They stayed just 21 hours on the moon, collecting rocks, placing instruments, and leaving behind a plaque that reads, "We came in peace for all mankind." And then they came home. The footprints are still there, undisturbed, untouched, pressed into ancient dust that hasn't moved in billions of years. So tonight, as your thoughts grow softer, imagine those prints under moonlight, quiet, empty, and eternal. How Mars rovers survive, think, and explore on their own. Imagine being alone on another planet. No one nearby, no one to talk to. The sun rises cold over dusty red plain, and the only thing moving is you, a machine, awake and alert in the stillness of Mars. But you're not helpless. You're not waiting for someone to drive you like a remote-controlled toy. You think. Mars rovers are not just tools. They're explorers, built with enough intelligence to make choices, navigate danger, and carry out science without constant human input. When commands arrive from Earth, it's often too late to react in real time. The signal takes up to 20 minutes to cross the void. So, the rover must be ready. It scans the terrain, measures slopes, checks for rocks or sand traps. If a path is too steep or risky, it chooses another. It watches the sky, tracks the position of the sun to recharge its solar panels, and adjusts its energy usage based on the Martian day. Its cameras are its eyes. Its robotic arm is a geologist's hand. Its memory stores maps, coordinates, and targets. And even though it can't feel the wind or smell the dust, it senses radiation, temperature, texture. In 2021, Perseverance used onboard AI to drive farther in one day than any rover before it, over 100 meters across uncertain terrain, completely on its own. And when night falls, the rover goes to sleep. It powers down, conserves energy, waits for sunlight. It doesn't get lonely. It doesn't dream. But it's there, working, watching, learning. As you fall asleep tonight, imagine it, a small, quiet traveler on a vast, empty world, thinking, listening, rolling forward, one careful wheel at a time. Where do elements like gold and platinum come from in space? You might be wearing some right now, a ring, a chain, a bit of gold glinting on your skin. It feels precious, rare, timeless. But where did it come from? Not from Earth. Not really. Gold is older than our planet. Most of the elements we know, carbon, oxygen, iron, were formed inside stars. In their final moments, when a star dies in a fiery supernova, it releases those elements into space. That's how planets are born. That's how life begins. But gold is different. It needs something even more violent, something more rare. Gold, along with platinum and other heavy elements, is born in the collision of neutron stars, the densest objects in the universe, just a few kilometers wide, but heavier than the sun. When two of them spiral into each other and merge, the explosion is so intense that it forges the heaviest atoms we know. In 2017, astronomers actually saw it happen, not just with telescopes, but with gravitational waves. It was the first time we watched the birth of gold in real time. After that, the particles drifted, cooled, gathered into dust. Eventually, that dust became stars and planets, and somewhere deep in the crust of the early Earth, it settled, waiting to be found. So that ring, that shimmering dot in a bracelet or necklace, it began in a cosmic explosion hundreds of millions of years ago, forged in fire, delivered by time. Tonight, as you settle under the blankets, think of that. You're not just made of stars. You carry their treasure. The story behind the pale blue dot photo. It's one of the most famous images ever taken. But when you first see it, it seems almost empty. A soft golden haze, a few scattered streaks of light, and there, barely visible, a tiny dot, less than a pixel, pale blue. That's The image was captured in 1990 by the Voyager 1 spacecraft. from almost 6 billion kilometers away. It had already passed the orbits of all the outer planets and was about to leave the solar system forever. But before it drifted into interstellar space, astronomer Carl Sagan made a request. Turn Voyager around. Let it take one last picture of home. What came back was haunting. No continents, no clouds, no people. Just a faint blue speck, caught in a shaft of scattered sunlight, suspended in a beam like dust in the air. And yet, everything is there. Every moment in history, every mountain and ocean, every family, every war, every poem, every child, every whisper, every hope. Carl Sagan later wrote, "Look again at that dot. That's here. That's home. That's us." It reminded us how small we are and how rare, how precious a world can be, even when it vanishes into cosmic silence. So tonight, as you lie in the dark, think of that image, the pale blue dot floating in the endless black. And remember, even the faintest light can carry the weight of everything. Could we terraform Mars? And what would it take? It's red, cold, dry, and quiet. Mars has always looked a little like home. The valleys, the polar ice caps, the traces of ancient rivers. But if we ever want to live there, truly live there, we'll have to change it. We'll have to terraform it. That means reshaping an entire planet, giving it air, warmth, water, a sky we could breathe beneath. Some scientists imagine giant mirrors floating in orbit, focusing sunlight onto the poles, melting the ice and releasing carbon dioxide into the atmosphere, thickening it, warming it. Others propose sprinkling dark dust on the ice caps to make them absorb more heat. Still others talk about greenhouse factories, pumping out gases that would trap warmth, slowly building pressure, degree by degree. Over centuries, maybe thousands of years, the surface might warm, liquid water could return, algae could take hold. Later, plants, then maybe forests, one day even oceans. But the truth is, terraforming Mars isn't just a technical challenge, it's a philosophical one. Should we change another world? Should we leave Earth's fingerprint on something that's been untouched for billions of years? Or is this what life does? Reach out, adapt, expand. No one knows the answer yet, but the idea remains, glowing quietly in our imagination. So tonight, picture that future. Green valleys on Mars, air gently moving across a planet that was once silent, a second home built from patience, science, and dreams. And somewhere in that future, a child looking up at two moons, wondering what Earth must look like. What happens if you fall into a gas giant? Imagine floating above a massive planet, more massive than anything in our solar system except the Sun. Below you is Jupiter, or maybe Saturn, a gas giant, swirling, beautiful, mysterious. Now, imagine falling in. At first, the clouds seem soft, like whipped cream stretched across 1,000 kilometers. Bands of color spin below you, orange, white, red. A storm the size of Earth churns in the distance, never stopping. As you descend, there's no surface to land on, no ground, just more atmosphere, thicker, darker, heavier. You fall through ammonia clouds, then water vapor, then deeper into layers of hydrogen and helium. pressure begins to build, your body, or even a spacecraft, wouldn't last long. Soon, the pressure becomes crushing. Temperatures rise to thousands of degrees. Hydrogen, once a gas, becomes liquid. And deeper still, it turns into something strange. Metallic hydrogen, a substance that may conduct electricity better than anything on Earth. Deeper again, and you're approaching the core. Maybe a dense ball of rock and metal, or maybe something we can't yet imagine. No probe has ever made it this far. The data fades. The models break down, because no one really knows what lies at the heart of a gas giant. It is one of the universe's quiet mysteries, a place so vast and hostile, and yet so beautiful from afar. So as you sink into sleep tonight, imagine that fall. Endless, soft, slow, down through colors and clouds, into silence, into pressure, into the unknown. What is the Fermi paradox, and why haven't we met anyone yet? The universe is vast, so vast that it's almost impossible to imagine, filled with billions of galaxies, each with billions of stars, many of which have planets. Some like Earth, some older than Earth, some maybe even better. So, where is everybody? That question is at the heart of the Fermi paradox, a quiet contradiction that haunts astronomers. If the universe is so full of possibilities, why haven't we seen a single sign of intelligent life? It was first asked, casually, in a cafeteria in 1950 by physicist Enrico Fermi. Over lunch, he wondered aloud, "Where is everyone?" And no one had an answer. Since then, people have searched. We have scanned the sky for radio signals. We've looked for patterns in starlight. We've imagined alien civilizations building giant structures around stars, colonizing entire galaxies, or hiding in plain sight. But so far, nothing. Just silence. Maybe we're early. Maybe we're rare. Maybe civilizations rise and fall quickly, like flashes in the dark. Or maybe we're just not looking the right way. Some scientists believe intelligent life avoids contact. Others think we've already been noticed, but we're not ready yet. And then there's the quietest possibility. Maybe we really are alone. But even that silence tells a story about how precious life is, how improbable, how fragile, and how special it is that on one pale blue dot, there's someone, you, wondering about the stars. As you drift deeper into sleep, let that question float with you. If the universe is filled with voices, why do we hear only our own? How long until the sun burns out? The sun feels eternal. It rises every morning. It warms our skin. It feeds the plants, lights our skies, and anchors the entire solar system. It's so constant that it's easy to forget. The sun is a star, and like all stars, it has a life. Right now, it's about halfway through. Our sun is around 4.6 billion years old. It burns by fusing hydrogen into helium in its core, a process that releases immense energy. But that hydrogen won't last forever. In about 5 billion more years, the sun will begin to run out of fuel. When it does, it will swell into a red giant, larger than Earth's orbit. It will engulf Mercury, Venus, maybe even Earth. After that, it will shed its outer layers, leaving behind a dense, glowing core. A white dwarf, no longer burning, just fading slowly into darkness over trillions of years. But don't worry, there's time. By the time the sun begins to change, humanity, if it still exists, may be living on other worlds. We may have left the solar system entirely, carrying with us the memory of the light that first warmed our species. So tonight, as you lie beneath its invisible glow, remember, the sun you see in the day sky is ancient, but steady. It has billions of quiet mornings left, billions of golden afternoons, and for now, it's here, burning gently, holding us close. How do we know the universe is expanding? The night sky feels still. The stars seem fixed like tiny holes in a vast, unmoving ceiling. But the truth is more surprising and more beautiful. The universe isn't just sitting in place, it's growing. We know this because of something called redshift. When we look at distant galaxies, their light appears stretched, shifted toward the red end of the spectrum. It's the same effect you hear when a siren passes by and changes pitch. The sound stretches as it moves away. Galaxies are doing the same thing, but with light. And the farther away they are, the faster they seem to be moving from us. It's not because we're at the center. It's because space itself is stretching in all directions. This discovery was first made in the 1820s by Edwin Hubble. He noticed that every galaxy, almost without exception, was retreating, not drifting through space, but carried by it, like raisins in rising dough. And here's the wonder. If the universe is expanding now, that means long ago, it was smaller, more compact, which leads us to the Big Bang, not an explosion, but a beginning, a single point from which everything stretched outward. Time, matter, light, all of it. Even now, billions of years later, space is still expanding, quietly, softly, beyond what we can see. And you, lying still in bed, are drifting too, gently, silently, through an ever-growing universe. So tonight, as you sleep, imagine that motion, galaxies blooming like flowers, space unfolding like silk, and the whole cosmos breathing in slow, endless rhythm. What space-time actually means. Explained simply, time feels like something separate. It ticks, it passes, it flows. And space, that's everything around us, the distance between you and the stars. But what if they're not separate at all? What if they're the same thing? That's the idea behind space-time, a concept at the heart of Einstein's theory of relativity. It sounds complicated, but imagine this. Picture a large, soft sheet, like a trampoline stretched tight. That sheet is space-time. When you place something heavy on it, like a planet or a star, the fabric bends. Other things like comets or light beams move along those curves. Gravity, then, isn't just a force pulling things together. It's the shape of space-time itself, warping around mass. Even time bends, closer to something massive, like a black hole. Time actually slows down. Minutes stretch, clocks tick more slowly. Farther out, time speeds up again. It's not science fiction. We've measured it. Your phone's GPS even corrects for this difference between Earth's surface and orbit. So when we say space-time, we mean the woven fabric of everything. Height, width, depth, and time too. A single thing. Stretchable, shapeable, alive in a quiet, invisible way. And you, just by existing, are pressing gently into that fabric, leaving a dent, a presence, a path. As you drift into sleep tonight, imagine that, yourself floating in a sea you can't see, surrounded by gentle curves in space and in time. Where does a black hole go? What's beyond the event horizon? Somewhere far away, or maybe not so far, a star has collapsed. It's no longer burning, no longer shining. It's fallen inward, crushed by its own gravity, until nothing could stop it. What's left is a black hole. From the outside, it looks quiet, simple, a dark sphere floating in space. But at its edge, something strange happens. A boundary called the event horizon. It's the point of no return. Cross it, and you're gone. Not torn apart instantly, not exploded, just erase. No signal can escape, no light, no information. And that leads to a haunting question. Where does everything go? Inside a black hole, all our physics begin to break down. Space and time themselves twist. The core, what we call the singularity, is a place where gravity is infinite and the known rules of reality vanish. Some theories suggest that everything falling into a black hole is crushed into that point forever. Others wonder if black holes could be portals to other places, other dimensions, or even other universes. There's also the idea that the information isn't lost at all, that it's stored somehow in the surface of the event horizon, a kind of cosmic memory written in the fabric of space. We don't know yet. Maybe we never will. But black holes aren't monsters. They're not evil. They're simply gravity, taken to its extreme. And even they, over trillions of years, will fade, evaporating slowly into nothing. So tonight, let your thoughts fall gently, like stardust, toward the edge of the unknown, not with fear, but with wonder, because sometimes, even in the dark, the universe is still listening. How big is the universe, and could it be infinite? Stand outside on a clear night and look up. The sky seems endless, but how big is it really? The observable universe, the part we can actually see, stretches out about 46 billion light years in every direction. That's not because the universe is only that old. It's because space itself has been stretching, expanding faster than light can catch up. So what lies beyond that edge? We don't know. Maybe just more galaxies. Maybe something stranger. But here's the astonishing part. There's a real possibility that the universe is infinite. No edge, no center, no boundary. Just more stars, more space, more time, more everything. And in that infinity, Earth is smaller than a grain of dust. Your body, a flicker of molecules. Your life, a blink. And yet, here you are, thinking about it, part of it. Some scientists imagine the universe as a closed loop, like the surface of a balloon, finite but unbounded. Others think it may go on forever in all directions, with no repeating patterns, no familiar edges. And beyond even that, there may be other universes, a multiverse, bubbles of reality floating in something even larger. It's overwhelming, it's humbling, but it's also beautiful, because no matter how vast it is, your thoughts can still reach it. your questions can still stretch into that darkness. And even as you lie still, your mind moves outward, endlessly. So tonight, let it drift. Let your dreams stretch into that great silence, into the stars beyond stars, into the possibility that there may be no end at all. The sound of a black hole, how we heard it in B-flat space, is silent. There's no air to carry sound waves, no wind to whistle, no ocean to roar, just vacuum, just light, just silence. And yet, in 2003, scientists at NASA did something extraordinary. They heard a black hole, not with microphones, but with math. Deep in the Perseus galaxy cluster, 250 million light-years away, lies a supermassive black hole. Around it, clouds of hot gas, dense enough, massive enough to vibrate. Those vibrations rippled outward in slow, deep waves, pressure waves, technically sound. The note they detected was a B-flat 7 octaves below middle C, far too low for human ears. A sound so deep it would take millions of years to vibrate once, but it's there, still echoing, still humming, like the bass line of the cosmos. Years later, NASA used data from other telescopes to sonify black hole activity, translating energy patterns into sound humans can perceive. The result? A haunting melody, rising and falling almost like a voice, a whisper from gravity itself. Black holes don't just pull in light, they shape the space around them, the time, and maybe, in their own way, the music. So tonight, as everything grows quiet, imagine the sound beneath silence, a note stretched across galaxies, a black hole singing not in chaos, but in harmony. And somewhere in the stillness of your room, that sound, impossibly deep, impossibly slow, hums softly in your dreams. What if Earth had rings like Saturn? Close your eyes and picture the sky, not empty, but glowing. Not just stars, but giant arcs of light stretching from horizon to horizon. Pale gold, soft silver, a halo wrapped around the Earth itself. What if Earth had rings, like Saturn? It's not impossible. In fact, some scientists think Earth may have had rings long ago, formed after ancient collisions, then lost over time. But what if they stayed? The rings would hover above the equator fixed in the sky. If you lived near the poles, you might barely see them, just a sliver. But closer to the equator, they'd be breathtaking. Bands of ice and rock, thousands of kilometers wide, glowing with reflected sunlight. Cities would be built facing them. Cultures would grow up beneath their shimmer. Art, mythology, even timekeeping might change. Nights would never be truly dark. The moon might pass behind the rings or cast shadows through them. Eclipses would become layered events. Sunlight, moonlight, ring light, all overlapping in quiet choreography. But there would be trade-offs. Rings would block satellite orbits. Space travel would be harder. Their debris could threaten stations or even fall into the atmosphere. They'd shape not just our skies, but our technology, our ambitions. Still, the beauty would be impossible to ignore. So tonight, imagine Earth with rings, the way Saturn wears them. Elegant, silent, suspended above the clouds like a crown of frozen light. And somewhere beneath that glow looking up. Could there be oceans beneath the surface of distant moons? Not every ocean reflects sunlight. Some are hidden, locked beneath ice, tucked away on silent, frozen moons orbiting distant planets. Places like Europa, a moon of Jupiter, or Enceladus, orbiting Saturn. On the surface, they look like snowballs, white, cracked, lifeless. But beneath that crust, something stirs. Liquid water, oceans, vast and deep. We know this because of tiny signs, geysers erupting from cracks, spilling water vapor into space, magnetic fields wobbling strangely, hinting at salty seas below, heat radiating from the inside, enough to melt ice, even this far from the sun. Enceladus, no larger than the state of Arizona, shoots plumes of water hundreds of kilometers high. NASA's Cassini probe flew through one. It tasted the spray. Inside, complex organic molecules, the building blocks of life. Europa too may hide an ocean twice the volume of all Earth's seas. Under kilometers of ice, there could be warmth from tidal forces, minerals from the rocky core, a gentle darkness where life might begin. Not life as we know it, not fish or whales, but perhaps something simple, alien, waiting. It's a haunting thought that in the coldest places there may be warmth, in the darkest places a chance for life. So tonight, let your thoughts sink gently downward, beneath ice, beneath silence, into a world lit only by chemistry and pressure, a sea without sunlight, but not without wonder. How would it feel to watch Earth rise from the moon? Imagine standing on the moon. Beneath your boots, the ground is gray and silent, a desert of dust and shadows. The sky above you is black, even in daylight. No atmosphere, no breeze, just stillness. Now look toward the horizon, and rising slowly, impossibly, is Earth, not the moon in your sky, small and silver, but Earth, full, round, glowing blue and white, oceans swirling, storms drifting, continents you could name from here. It happens because the moon doesn't rotate the way Earth does. From most places on its surface, the Earth just hovers, fixed in the sky. But from a spacecraft in orbit around the moon, like Apollo 8 in 1968, you can see something breathtaking: Earthrise. It was astronaut Bill Anders who captured the famous photo, a blue marble lifting above the lunar limb, wrapped in cloud and light. He later said, "We came all this way to explore the moon, and the most important thing we discovered was the Earth." That moment changed how we see ourselves. It made our planet feel fragile, united, alive. No borders were visible, no politics, just one world, floating in darkness. So tonight, close your eyes. Imagine looking up, not at the moon, but at your own home. Rising slowly into view, not as a map, not as a globe, but as a single shimmering miracle, small, spinning, shared. Could a star live for 1 trillion years? What are red dwarfs? Not all stars burn bright and fast. Some live slow, quiet lives, glowing faintly in the dark for billions, even trillions of years. These are red dwarfs, the most common type of star in the universe. Small, cool, steady. If our sun is a blazing campfire, a red dwarf is a candle, gentle but lasting. They burn hydrogen with incredible efficiency, while large stars use up their fuel quickly and die in dramatic explosions. Red dwarfs stretch their lifespans across unimaginable time. The smallest of them could live for 1 trillion years. That's over 70 times the current age of the universe. In fact, no red dwarf has ever died. Not yet. The cosmos simply isn't old enough. That means, in the distant future, when all the bright stars have faded, when galaxies have grown dark and silent, red dwarfs will still be shining, slowly, faithfully, lighting the last chapters of the universe. Some of these stars have planets. Some of those planets are in the habitable zone, not too hot, not too cold. And though life around a red dwarf would face challenges, like solar flares and tidal locking, it's possible that someone, someday, could call such a place home, a quiet world around a quiet star. So tonight, let your thoughts drift toward the far future, past everything we know, into an age of deep time, where little stars still flicker, still warm, still shine, not loud, not fast, but lasting. What happens to time on a space station? Time feels constant, steady, familiar, but up there, in orbit, circling hundreds of kilometers above Earth, time bends, just a little. On the International Space Station, astronauts orbit the planet every 90 minutes. They see 16 sunrises and sunsets in a single day, and though their clocks tick almost the same as yours, they don't tick exactly the same. Because of Einstein's relativity, time behaves differently depending on speed and gravity. The faster you move, the slower time passes for you. The farther you are from a planet's gravity, the faster time flows. So, in orbit, where astronauts are moving incredibly fast and are slightly farther from Earth's gravity, they experience time just a touch differently. Each day, they gain about 0.1 seconds compared to people on Earth. It's barely noticeable, but it's real. So real, in fact, that GPS satellites must constantly correct for these differences, or our maps and navigation would quickly fall apart. Time isn't rigid. It flows, stretches, bends, depending on where you are, how fast you move, and what surrounds you. So picture an astronaut floating softly in the cupola of the space station, watching Earth spin silently below, everything moving, everything glowing, and around them, time slipping just a little bit slower. Tonight, as your own time slows into sleep, imagine yourself there, weightless, drifting, watching the hours pass not with numbers, but with light, sunrise, sunset, earthlight, dreamlight. Titan, a world with lakes of methane among Saturn's many moons. There is one that stands apart, not for its brightness, not for its size, but for something far stranger. Titan is the only moon in the solar system known to have a thick atmosphere, even denser than Earth's. When the Cassini spacecraft arrived in orbit around Saturn, scientists turned their instruments toward this orange, hazy sphere. What they found defied expectation. Titan has lakes, rivers, even rain, but they're not made of water. They're made of methane. On Earth, methane is a gas, a flammable, invisible component of natural gas. But on Titan, where temperatures hover around minus 180 degrees Celsius, methane behaves differently. It condenses. It rains from the sky. It carves channels into the icy surface. It pools in massive basins, the largest of which, Kraken Mare, is bigger than the Great Lakes combined. Imagine that, standing on the edge of a black, mirror-like sea, under a sky the color of rust, watching drops of liquid methane fall silently onto frozen ground. Titan's atmosphere is made mostly of nitrogen, like Earth's, but laced with methane and other hydrocarbons. Sunlight, faint though it is at that distance, triggers chemical reactions high in the atmosphere, creating a smog-like haze. This haze hides the surface from view, making Titan appear featureless from afar. But beneath that veil lies a landscape both familiar and alien. Dunes ripple across its equator. River channels snake toward lakes. There may even be cryovolcanoes, volcanoes that erupt not lava, but slushy mixtures of water and ammonia. In 2005, the Huygens probe descended through Titan's clouds. For 2.5 hours it fell, measuring temperature, pressure, and composition before landing on solid ground. It sent back the first images ever taken from the surface of a world drenched in liquid gas. And here's what's truly strange. Titan may be the only place, other than Earth, with a working cycle of liquid rain, erosion, evaporation, and clouds. Not water, but methane, a mirror of Earth frozen and reversed. And deep beneath its crust, scientists suspect, lies an ocean of liquid water, perhaps warm enough to support life. So tonight, imagine a world where lakes glisten in eternal twilight, where methane rains like water, and where alien life might one day ripple just beneath the surface. The coldest place in the universe, and how we found it. There are places in the universe where stars are born in fire, where galaxies collide, where energy floods every corner of space. And then, there are places of silence, stillness, cold beyond imagination. In 2003, astronomers pointed a telescope toward the constellation Centaurus, not searching for brightness, but for emptiness. And there, 5,000 light years away, they found something astonishing. A small, dim nebula, so faint it almost vanished into background noise. They named it the Boomerang Nebula. At first, it looked like just another dying star, shedding its outer layers in the final stages of its life. But as scientists studied it more closely, they realized this wasn't ordinary. The gas flowing from this object wasn't just expanding. It was expanding so quickly that it cooled to an impossible level. This quiet cloud of gas is colder than anything we've found in nature, colder than the vacuum of space itself. How cold? About 1 degree Kelvin. That's just a single degree above absolute zero, the point where all atomic motion nearly stops. In the vastness of the universe, even the cosmic microwave background, the leftover glow of the Big Bang, is warmer, sitting at about 2.7 Kelvin. And yet, this dying star managed to create a pocket of even deeper cold, not with magic, with motion. As gas rushes out from the center of the Boomerang Nebula, it expands rapidly, and just like air from a can of compressed gas feels cold as it escapes, this expansion cools the material to extremes. The process is called adiabatic cooling, a quiet, natural refrigeration system powered by the breath of a dying star. It's haunting to think about. A star at the end of its life, wrapped in a cloud so cold it defeats the temperature of deep space, and it won't last. Eventually, the gas will thin, the expansion will slow, and the nebula will warm again, losing its title as the coldest known place in the universe. But for now, it floats in silence, invisible to human eyes, unimaginably cold, a final whisper from a fading light, drifting quietly in the dark. And tonight, as your thoughts settle into stillness, that whisper joins you, a story made of ice, of motion, and of cosmic quiet. The Voyager Golden Record, a message to the unknown. In 1977, 2 spacecraft were launched into the dark, Voyager 1 and Voyager 2. Their mission was to explore the outer planets, but behind that mission was something quieter, stranger, and more poetic. Tucked inside each spacecraft was a small golden disk, smooth, reflective, about the size of a vinyl record. Not for navigation, not for science, but for communication. The Voyager Golden Record was created as a time capsule, a greeting, a message in a bottle cast into the cosmic sea. It contains the sounds of Earth, the crash of waves, a baby crying, footsteps, a kiss, music from across cultures and centuries, Beethoven and Bach, traditional songs from Senegal, Japan, Peru, greetings spoken in 55 languages, and one line recorded in English. Hello from the children of planet Earth. Etched onto the disk is a diagram, a map of sorts, showing how to find our solar system using pulsars. There's also a guide explaining how to play the record, using only pictures, because if it's ever found, it may be by someone who doesn't know what a record is, or what a human is. Carl Sagan and a small team spent over a year deciding what to include. They had to choose a single photograph of a mother with her child, a single poem, a single heartbeat. They knew the odds were low that anyone or anything would ever find it, but still, they sent it. Today, Voyager 1 is more than 24 billion kilometers from Earth. It's left the solar system entirely, drifting into interstellar space. The Golden Record goes with it, silent, unpowered, unchanged. It may float forever, for millions of years, through dust and distance, past stars that haven't formed yet. And if someone, somewhere, ever finds it, they will hear us, not just our science, not just our facts, but our voices, our music, our wish to be known. So tonight, imagine that, a golden disk tumbling through the black, still whispering softly across time. This is who we were. From a golden disk drifting through silence, let's move closer again, to a world we know well, yet barely understand. A giant wrapped in clouds and hidden power. Oumuamua, the interstellar visitor that changed everything. In October 2017, astronomers in Hawaii spotted something strange. A faint object moving quickly through the sky, too fast, in fact, to be from here. They called it Oumuamua, a Hawaiian word meaning scout or messenger from afar arriving first. It was the first confirmed object ever observed passing through our solar system from interstellar space. At first, it looked like a comet, but it had no tail, no visible gas. Then it was labeled an asteroid, yet its motion didn't quite fit. It accelerated slightly as it moved away from the sun, behaving in ways no ordinary rock should. What made it even stranger was its shape, Calculations suggested Oumuamua was long and narrow, maybe 10 times longer than it was wide. Some scientists imagined a cigar-shaped rock, tumbling end over end. Others proposed a thin, flat disk, like a piece of space debris. Either way, it was unlike anything we'd seen, and it moved fast, too fast to stay. Oumuamua came in from beyond the orbit of Neptune, swung around the sun, and was gone back into interstellar space before we could even launch a proper mission to chase it. It didn't leave a trail, just data, just debate. Some researchers believe it was a fragment of a planet torn apart in another star system. Others suggest it was a strange kind of icy body, shedding invisible hydrogen as it warmed. And a few, cautiously, have asked whether it could have been artificial, a probe, a sail, a fragment of alien technology. We may never know. What we do know is this: the universe is not empty between the stars. There are travelers, fragments, drifters, and now we know to look for them. In 2019, astronomers spotted a second interstellar object, a comet named 2I Borisov. More will come. Some might be stranger still, and maybe one day we'll catch one in time. But for now, Oumuamua continues its silent journey out of the solar system, away from the sun's pull into the dark between stars. So tonight, let your thoughts follow it, past planets and gravity, into the deep unknown. A quiet visitor, never stopping, never returning, and still unexplained. We've talked about objects that pass through space, but now, let's pause and imagine what space itself is like, not just to see, but to sense. If you could stand at the edge of a spacecraft, what would it smell like after the airlock opens? What is cosmic background radiation, and why it still glows everywhere you look in space? Even in the darkest direction, something is there. Not stars, not galaxies, but light, faint, ancient, uniform. It's called the cosmic microwave background, a quiet glow that fills the universe, not because of anything happening now, but because of something that happened over 13 billion years ago. In the beginning, the universe was not cold and silent. It was dense, hot, blinding, a soup of particles and light so energetic that nothing could move freely. Photons, particles of light, were constantly bouncing, colliding, trapped in a fog of plasma. But as the universe expanded, it cooled, and after about 380,000 years, something profound happened. Atoms formed. When that happened, the fog lifted. Light was finally free to travel, and that very first light, released across all directions, has been moving ever since. It's stretched by the expanding universe, cooled by time, and now it appears not as brilliant light, but as gentle microwaves, low-energy radiation, a whisper from the edge of time. In 1965, two radio engineers, Arno Penzias and Robert Wilson, stumbled upon it by accident. They were trying to eliminate noise from their antenna, but no matter what direction they pointed it, a faint hiss remained. That hiss was the echo of the Big Bang. Since then, satellites like COBE, WMAP, and Planck have mapped this background radiation in astonishing detail. It's not perfectly smooth. There are tiny variations, small ripples in temperature, no more than a few millionths of a degree. But those ripples are crucial. They're the seeds of everything. Those tiny fluctuations are what allowed gravity to pull matter together, forming clouds, stars, galaxies, and eventually us. The cosmic background is everywhere. You could tune an old television between channels, and part of the static you'd see would be its signal, a fragment of the universe's first light reaching you through time. And it's still glowing, not with heat or color, but with memory. So tonight, imagine the dark sky above you, not empty, but filled with the oldest light in existence, a glow that began when the universe took its first breath and never stopped. From the ancient light still echoing across the universe, let's return to something more recent, something that drifted into our solar system unexpectedly and left behind only questions. Jupiter's magnetic field, stronger than anything on Earth. Jupiter is the largest planet in our solar system, a swirling storm world, striped in color, with moons that orbit like miniature planets. But size alone isn't what makes it so overwhelming. What surrounds Jupiter is invisible, but immense. It has the strongest magnetic field of any planet we've ever measured, nearly 20,000 times stronger than Earth's. And that changes everything around it. The source of this magnetism lies deep beneath Jupiter's clouds. Unlike Earth, which has a solid metal core, Jupiter is made mostly of hydrogen. But under the weight of its massive atmosphere, that hydrogen becomes compressed. At incredible pressure, it transforms into a rare form, metallic hydrogen, a fluid that conducts electricity like a metal. That liquid layer rotates rapidly, and just like a dynamo, it generates a magnetic field that reaches far beyond the planet itself. Jupiter's magnetosphere, the area controlled by this field, is so large it would appear bigger than the sun if we could see it in the sky. It traps particles, bends radiation, and shapes the environment for millions of kilometers in every direction. It also creates something beautiful. Around Jupiter's poles, charged particles spiral along magnetic lines, colliding with atoms in the upper atmosphere. The result is a glowing aurora, like Earth's northern lights, but far more powerful. These auroras shine not just in visible light, but in X-rays and ultraviolet. They flicker constantly, like the heartbeat of a planet made of storm and force. But this magnetic power is also dangerous. Radiation near Jupiter is intense, hundreds of times stronger than what would be safe for humans. It can damage spacecraft, destroy electronics, and pose serious challenges to future missions. Even the Galileo probe, designed for this environment, suffered from it. And yet, studying it reveals not only Jupiter itself, but how magnetic fields shape planets and space. It's a reminder that what we cannot see can still be massive. And in the quiet of space, forces still swirl, pulse, and shimmer in unseen rhythms. So tonight, as you close your eyes, imagine that silent giant turning slowly, wrapped in invisible strength, surrounded by glowing storms we'll never hear, but can almost feel. Now, from Jupiter's storms and magnetism, we drift even farther, beyond planets and moons, beyond stars and dust, to something older than galaxies, a glow that began when time itself was still young. Can you smell space? What astronauts actually say space is a vacuum, a place without air, without pressure, without smell, at least in theory. But astronauts who've walked in space tell a different story. They don't smell space directly, of course, You can't take off your helmet and inhale, not without deadly consequences. But when they return from a spacewalk and re-enter the airlock, something unusual happens. As they remove their suits, as air floods back in and particles dislodge from their gear, a scent appears, and they all describe it in eerily similar ways. Some say it smells like burnt metal. Others say welding fumes, hot gunpowder, charred steak, ionic ozone, a sharp, distinct aroma that lingers in the air of the station just after EVA, extravehicular activity. So where does this smell come from? One theory is that high-energy particles in space, cosmic rays, ultraviolet light, solar wind, interact with materials on the outside of the suit. They leave behind reactive molecules. When those molecules are suddenly exposed to oxygen inside the spacecraft, they oxidize and produce that burned, metallic scent. It's not perfume, it's chemistry. The smell of energy, impact, and molecular rearrangement. The International Space Station isn't the only place astronauts have noticed it. Apollo crews described a similar scent after returning from the moon. The lunar dust they brought back into the cabin smelled of spent fireworks, dry, smoky, almost electric. Even spacecraft themselves carry traces of this aroma. Engineers on Earth say the inside of old return capsules, like those from Soyuz missions, often bear that same scorched, faintly sweet smell. It's subtle, but unforgettable. And now, it's become a kind of signature, the invisible evidence that someone has touched the void and come back. So while space may be silent, it's not entirely without presence. There is a smell, a trace, a memory clinging to fabric and metal. And tonight, as you lie still, imagine the hush of the airlock, the hiss of pressure equalizing, and that sudden, curious scent of space, ghostly, metallic, impossible, drifting through the air one breath at a time. From the subtle scent of space, we now turn our gaze outward, far beyond the solar system, beyond the familiar stars. Because recently we opened a new kind of window and looked farther into time than ever before. The James Webb Deep Field. Looking back in time, in July 2022, a single image changed the way we see the universe. It wasn't colorful at first glance, no planets, no glowing nebulae, just a dark frame, dotted with delicate arcs and pale red points. But those points, each one, was a galaxy, not stars. Galaxies, thousands of them, layered across cosmic distance. This was the James Webb Space Telescope's first deep field, a long, detailed exposure of one tiny patch of sky, a portion so small it could be covered by a grain of sand held at arm's length, and yet, within it, entire histories of light. What made this image so special wasn't just how many galaxies it revealed, but how far back in time it looked. Light travels fast, but not instantly. The farther away something is, the older the light we see from it. And some of the galaxies in this image are so distant that their light began its journey over 13 billion years ago, just a few 100 million years after the Big Bang. That means we're not just seeing faraway objects, we're seeing ancient ones. Some of the galaxies Webb captured are among the earliest ever formed, tiny, irregular, clumpy, unlike the grand spirals we know today. They're snapshots from a time when stars were still young, when the first heavy elements were just beginning to form. And the way the telescope sees them is different too. James Webb doesn't look invisible light. It sees in infrared wavelengths that pass through dust, that stretch as the universe expands. That's why it can glimpse what other telescopes miss: the hidden, the red shifted, the faint echoes of cosmic dawn. In that single image, we see arcs caused by gravitational lensing, the bending of light around massive objects. We see merging galaxies, distant clusters, light shaped by gravity and time, and all of it quiet. So much silence, so much distance, and yet so much detail. So tonight, as you close your eyes, think of that narrow piece of sky, that small window filled with thousands of galaxies, each one a universe of stars, each one a memory, and beyond it, more, always more. After traveling so far through space and time, let's come closer again, to the edge of our own solar system, to a small icy world that once held a title and then lost it. Galaxies collide. What will happen when the Milky Way meets Andromeda? The night sky looks still, but it's not. Everything moves. Stars orbit, clusters drift, and galaxies, vast collections of billions of stars, glide silently through the dark, including ours. The Milky Way is on a collision course, not tomorrow, not next year, but in about 4 billion years, it will meet another spiral galaxy, Andromeda, a majestic swirl of stars, slightly larger than our own, visible from Earth as a faint smudge in the night sky. They're approaching each other at nearly 400,000 kilometers per hour. It sounds catastrophic, a galactic crash, but space is wide. Even in galaxies packed with stars, the distances between those stars are enormous. So when two galaxies collide, almost no stars actually touch. Instead, their gravity dances. As the galaxies approach, their shapes distort. Tidal forces stretch their arms, pulling streams of star into long arcs. Clouds of gas crash together, triggering bursts of new star formation. Cosmic fireworks, bright and short-lived. Eventually, the galaxies will merge. Over millions of years, their spirals will dissolve, and they'll form a new shape, likely an elliptical galaxy, rounder and smoother than what we see now. Some call the future result Milkomeda, a combination of both names. What will happen to Earth? By then, the sun will be nearing the end of its life. Life on Earth may have already moved on, or moved elsewhere. But if someone or something is still here, they might look up and see a sky filled with strange new stars, bright streams, twisting bands of light, the Andromeda core growing larger night after night, until the two galaxies swirl into one. And in the far future, even that new galaxy will drift, not toward anything, but away, because the universe itself is still expanding, still stretching space between galaxies that aren't gravitationally bound. So this collision, beautiful, slow, and inevitable, may be one of the last great gatherings of stars before isolation grows. Tonight, imagine that meeting. Not an explosion, not chaos, but two galaxies, full of light and memory, slowly becoming one. A silent dance across millions of light years. Galaxies rise and merge over billions of years, but within them, each star lives a much shorter story. Let's pause now and follow one of those stories from beginning to brilliant end. Why Pluto isn't a planet anymore. and why it still matters. For decades, children around the world learned a simple list: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto. 9 planets. Neat, predictable. But in 2006, that list changed. Pluto was reclassified, no longer considered a full-fledged planet, but instead given a new name: dwarf planet. The decision caused confusion, frustration, and even grief. Some felt like an old friend had been demoted, but behind the change is a story of discovery and of how science evolves. Pluto was discovered in 1930 by Clyde Tombaugh. From the beginning, it stood out. It was smaller than any other planet. Its orbit was tilted and stretched. It sometimes came closer to the Sun than Neptune, but it was accepted as the 9th planet, mostly because nothing else like it had been found. That changed in the early 2000s. Astronomers began discovering other small, icy worlds beyond Neptune. One of them, called Eris, was nearly the same size as Pluto. Some thought Eris might become the 10th planet. But if Pluto and Eris were both planets, what about the dozens of other similar bodies? Should we have hundreds of planets? The International Astronomical Union faced a choice: either expand the definition of a planet to include all these new objects, or refine it. They chose to refine. According to the new definition, a planet must: 1. Orbit the Sun. 2. Be nearly round due to its own gravity. 3. Clear its orbit of other debris. Pluto meets the first two, but not the third. Its orbit crosses paths with others in the Kuiper Belt, a region filled with icy leftovers from the early solar system. So Pluto was reclassified. Not gone, not erased, just understood differently. And yet, Pluto remains important. In 2015, NASA's New Horizons spacecraft flew past it for the first time. What it found was a complex, geologically active world, with ice mountains, nitrogen glaciers, and a heart-shaped plain. Small, but not simple. So tonight, as you rest, remember, sometimes things lose their names, but not their meaning. Pluto still drifts at the edge of our solar system, cold, distant, and quietly beautiful. Not just a dwarf planet, but a world with a story. From the outer edge of our solar system, let's look far beyond, to our home galaxy, and to something we know is coming, slow, silent, and inevitable. How stars die. White dwarfs, neutron stars, and supernovas stars don't live forever. They are born in clouds of gas and dust, shine for millions or billions of years, and then fade. But the way a star dies depends on how it lived, especially how massive it was. Let's start with a star like our Sun. Over time, its core will run low on hydrogen, the fuel that powers its light. As fusion slows, the core contracts and heats up. The outer layers expand. The star becomes a red giant, swollen and cooler, but still glowing. Then slowly it sheds its outer layers into space, forming a soft, glowing cloud, a planetary nebula. What remains at the center is small, dense, hot, a white dwarf, about the size of Earth, but with the mass of the Sun, so dense that a single teaspoon of it would weigh several tons, no longer fusing atoms, just cooling slowly over billions of years. like a cosmic ember. But not all stars go so quietly. More massive stars, 8, 10, 20 times the mass of our sun, live faster, burn hotter, and die more violently. When their cores can no longer sustain fusion, they collapse inward in an instant, triggering an immense explosion, a supernova. For a brief time, a single star can outshine an entire galaxy. The explosion sends elements into space: iron, oxygen, gold, the raw material for planets, for life. What remains behind depends on the mass. If the core is as us, but not too heavy, it becomes a neutron star, an object no bigger than a city, but denser than anything else in the universe besides black holes. So dense that protons and electrons are crushed into pure neutrons. A teaspoon would weigh billions of tons. Some neutron stars spin rapidly, sending out beams of radiation like a lighthouse. We call those pulsars. And if the core is even more massive still, gravity wins. The star collapses into a black hole, not an object, but a region of space where not even light can escape. So tonight, think of all the stars above you, some still shining, some already gone, each one born in fire, each one ending in silence or in light. And between those two moments, the history of everything. We've seen how stars end their lives in brilliance or collapse, but now, let's turn to something quieter. Two distant worlds, cold and overlooked, yet more mysterious than they seem. The ice giants. Why Uranus and Neptune are so strange. At the edge of our solar system lie two planets that often escape attention. They're not the largest, not the brightest, but they are among the most puzzling. Uranus and Neptune, the ice giants. Unlike Jupiter and Saturn, which are mostly hydrogen and helium, these two are rich in heavier elements: water, ammonia, methane. These compounds form icy slush deep within their atmospheres, giving them their name. But the mysteries go far beyond composition. Start with Uranus. It's tilted so far that it essentially rolls around the sun on its side. Its axis is tipped at 98 degrees, meaning its poles take turns facing the sun for decades at a time. No other planet does this. Why? Some scientists believe Uranus suffered a massive collision early in its history, a glancing blow from a protoplanet that knocked it sideways. That impact may have also disrupted its internal layers, creating a planet that spins like no other. Its magnetic field is tilted and off-center. Its atmosphere is quiet, oddly lacking in the dramatic storms seen on other gas giants. And its temperature, surprisingly cold. In fact, it's the coldest planet in the solar system, even colder than Neptune, which is farther from the sun. Neptune, by contrast, is wild. Its deep blue color comes from methane in its upper atmosphere, but beneath that lies dynamic weather, the strongest winds in the solar system, reaching speeds of over 2,000 kilometers per hour. In the 1980s, Voyager 2 captured images of a massive dark storm, the Great Dark Spot, a kind of hurricane larger than Earth. And yet, Neptune radiates more heat than it receives. Its interior is still warm, for reasons we don't fully understand. Some theorize a hot core or residual heat from formation. Others suggest unknown processes still at work deep below. These two worlds may hold clues to how planets form, not just here, but in exoplanetary systems across the galaxy. Many discovered exoplanets resemble ice giants, more than gas giants or Earth-like worlds. So tonight, as you drift into rest, picture those distant orbs, blue, quiet, spinning in darkness, tilted, stormy, cold, strange in ways we're still learning to describe. From the cold, tilting giants at the edge of our solar system, let's shift into something more speculative, an idea that stretches not just science, but imagination itself. What if, instead of living on planets, we lived around stars? What a day feels like on Venus. Wind, heat, and clouds of acid. This is the brightest planet in our night sky, often called the morning star or the evening star, about the same size as Earth, similar in mass, rocky, close, but standing on its surface would be like standing inside a furnace wrapped in poison. Let's imagine for a moment that you could survive there. The sky above is a thick pale yellow, not from sunlight, but from clouds of sulfuric acid swirling endlessly. They hide the sun completely. Daylight on Venus feels like twilight, filtered through smoke. But it's not cold, quite the opposite. Venus is the hottest planet in the solar system, even hotter than Mercury, which is closer to the sun. The surface temperature hovers around 465 degrees, hot enough to melt lead. That heat isn't from direct sunlight, but from its own atmosphere. A runaway greenhouse effect has trapped heat for millions of years. The air is not just hot, but heavy. The pressure on the surface is over 90 times greater than Earth's, like being 900 meters underwater. Every breath would be fatal. Every surface probe we've ever sent has been crushed, melted, or silenced within hours. And yet, the wind moves. High above the surface, in the upper atmosphere, clouds circle the planet at supersonic speeds, over 300 kilometers per hour. These high-altitude winds race ahead of the planet's slow rotation. Venus turns so slowly that a single day, from one sunrise to the next, lasts 243 Earth days. But strangely, a year on Venus is shorter, just 225 Earth days. Its day is longer than its year. If you were to watch the sun from Venus, it would rise in the west and set in the east, backwards, and do so once every 2/3 of a year. Despite its hostility, Venus is a point of fascination. Some scientists believe life may exist high in its atmosphere, where temperatures and pressures are less extreme. Others dream of floating cities in its upper clouds, habitats suspended above the heat, drifting like silent balloons. But on the ground, Venus remains silent, still, unreachable. So, tonight, imagine that distant world, glowing softly in our sky, hiding its violence behind beauty. A planet of heat, wind, and time that flows strangely. A world not built for us, but impossible to ignore. We've stood in the burning silence of Venus. But now, let's travel outward, past Mars, past Jupiter, past the final giant planets, out to the solar system's quiet edge, where sunlight weakens and something ancient waits in the cold. Could we live inside a Dyson sphere? The wild megastructure idea. In 1960, physicist Freeman Dyson proposed a thought experiment. If an advanced civilization wanted more energy than a planet could provide, why not capture the full power of a star? Not with solar panels on rooftops, but with a structure built in space that would surround the star and absorb its energy directly, This became known as the Dyson sphere. In science fiction, it's often imagined as a solid shell, a vast metal globe enclosing a star, with people living on the inner surface. But in reality, such a structure would be unstable. A solid sphere would collapse under its own gravity or drift dangerously. More realistic versions are lighter and looser. Some imagine a Dyson swarm, countless satellites orbiting in synchronized paths, collecting solar energy and transmitting it wirelessly. Others suggest a Dyson bubble, vast solar sails held in place by the balance between radiation pressure and gravity. The scale is almost impossible to grasp. To build even a partial Dyson swarm, you'd need more material than exists on Earth. Mining planets, dismantling moons, harvesting asteroids. It would take technology far beyond our own, and time measured in centuries. But the payoff would be enormous. Access to nearly 100% of a star's energy, enough to power megacities, interstellar travel, artificial worlds, perhaps even consciousness itself. Could it ever be real? Some astronomers think it's possible that Dyson-like structures might exist elsewhere. In fact, they've proposed searching for them, not by looking for the structure itself, but by detecting waste heat. A Dyson sphere would absorb starlight and re-emit it as infrared radiation. A star that looks dim in visible light, but unusually bright in infrared, could be a clue. In 2015, one star, KIC 8462852, also called Tabby Star, drew attention for its strange dimming patterns. Some speculated a Dyson swarm, others pointed to dust or comets. The mystery isn't fully solved, but the idea remained. Maybe, somewhere out there, someone has already done it. So tonight, imagine that, not living under a sky, but inside it. A civilization orbiting its star like bees around a flame. Endless light, endless structure, and the quiet hum of a machine built to cradle the sun. Let's leave behind imagined megastructures and return to something real and much closer. A planet that seems like Earth's twin from afar, but up close could hardly be more different. The Kuiper Belt, a frozen border around the solar system, far beyond Neptune, where the planets end and space seems to begin. There is a region that isn't empty. It's filled with ice, dust, remnants of early formation. This is the Kuiper Belt, a vast ring of frozen objects that circles the sun like a forgotten halo. It begins around 30 astronomical units from the sun. That's 30 times farther than Earth, and stretches out to about 50 AU. But it's not a wall. It's more like a fading field, full of debris left over from the birth of the solar system. Some of these objects are small, no bigger than rocks. Others are hundreds of kilometers wide. Pluto lives here. So does Haumea, shaped like an egg. Makemake, red and distant. And Eris, the object that helped force us to reconsider what the word planet really means. But these are just the ones we've named. Astronomers believe there are tens of thousands of Kuiper Belt objects, larger than 100 kilometers across, and perhaps millions more, smaller and silent, drifting in the dark. It's a place of low gravity, weak sunlight, temperatures near absolute zero, and yet it holds answers. Studying Kuiper Belt objects helps us understand the early solar system. These bodies are pristine, unchanged for billions of years. They've remained in cold storage since the time planets formed, preserving the chemistry and texture of ancient material. In 2015, NASA's New Horizons probe flew past Pluto, revealing a world of mountains, nitrogen plains, and surprising complexity. After that, it continued into the Kuiper Belt, reaching an object called Arakoth in 2019, a contact binary shaped like a snowman, untouched since the dawn of time. And still, the Kuiper Belt continues. Beyond it lies the scattered disk, and farther still, the Oort cloud, a sphere of icy bodies too distant to see. But the Kuiper Belt is the beginning of that vastness, the place where the structured solar system ends and the long night begins. So tonight, imagine it, countless icy fragments drifting slowly at the edge of everything, cold, ancient, silent, and yet always there. From the icy outskirts of our solar system, let's come closer again, not to planets or belts, but to something we see almost every night, a familiar face in the sky that never seems to turn. Tidal locking. Why the moon always shows the same face. Look at the moon. Any night, any season, any year, its shape may change, but its face stays the same. One side always faces Earth. The other, the far side, remains hidden from view, seen only by spacecraft. Why? Why doesn't the moon rotate like other celestial bodies? The answer lies in a quiet, powerful force, tidal locking. Long ago, the moon spun much faster. As it orbited Earth, its rotation wasn't synchronized, but Earth's gravity pulled on it unevenly, more strongly on the side facing us, less so on the far side. This created tidal bulges, stretching the moon slightly. As it rotated, those bulges tried to shift position, but gravity resisted. Over millions of years, this tug of war slowed the moon's rotation until it matched its orbit exactly. Now, it turns once on its axis for every orbit it completes. The result? We always see the same hemisphere, not because the moon doesn't rotate, but because it rotates perfectly in sync with its movement around us. Earth is doing the same to the moon, just more slowly. Over immense spans of time, our planet's own rotation is gradually decelerating. Days are getting longer, very slowly. Tidal locking is not instant. It's erosion in motion, gravitational memory. And the moon isn't the only place this happens. Many moons in our solar system are tidally locked to their planets. Charon, Pluto's largest moon, is so tightly bound that the two objects are locked to each other, always showing the same face in both directions, like a pair of dancers frozen mid-spin. Some exoplanets, orbiting close to their stars, may be tidally locked as well. That means one side bakes in constant daylight, while the other freezes in eternal night. And between them, a twilight line, perhaps the only habitable zone. So the next time you see the moon, remember its stillness is an illusion. It turns, it moves, it's simply locked, held in a rhythm so perfect, so slow that it feels like stillness. And tonight as you drift toward sleep, imagine that silent rotation, soft, balanced, unchanging, a quiet dance between worlds, still going on above you. We've watched the moon move in perfect rhythm with Earth, but now, let's go beyond the bodies themselves, to the spaces in between, invisible places, not made of matter but of balance. Can you see a black hole? How we photographed the unseeable. For most of history, black holes were invisible. not just because they were far away, but because, by definition, they don't emit light. No glow, no surface, just a shadow in space where gravity is so strong, not even light can escape. So how do you photograph something that can't be seen? You don't capture the black hole itself. You capture its effect. In 2019, the Event Horizon Telescope, a global network of synchronized radio observatories, released the first ever image of a black hole. It wasn't a telescope in space, but a collection of ground-based dishes scattered across the Earth in Chile, Hawaii, Spain, Antarctica, and more. Together, they acted like a planet-sized lens. They focused on a galaxy called Messier 87, over 55 million light-years away. At its center, a supermassive black hole, billions of times the mass of our sun. Around it, a swirling disk of hot gas and magnetic energy, spinning near the speed of light. That gas emits radiation, not from the black hole itself, but from just outside it, right at the edge of what's called the event horizon, the point of no return. What we saw in that now famous image was a glowing ring, brighter on one side due to the Doppler effect, where light is boosted by the speed of rotation. In the center, a dark patch, not empty space, but the black hole's shadow. It wasn't just a scientific achievement. It was confirmation. Decades of theory and simulation suddenly turned into a photograph, a picture of something we thought we'd never see. And in 2022, the same technique was used again, this time to image the black hole at the center of our own galaxy, the Milky Way. It's called Sagittarius A, quieter, smaller, but still extraordinary. Both images look blurry, imperfect, but in their fuzziness lies something powerful, visual proof of the most extreme phenomenon in nature. We didn't just detect it, we saw it. So tonight, imagine that glowing ring, not a fire, but a boundary, the edge of reality as we know it. And in the center, not darkness, but depth, a place where time slows, light bends, and space becomes something else entirely. We've just seen the edge of a black hole, a place where even light disappears. Now let's turn our attention outward again, toward the stars. Not to look, but to listen. Because for more than half a century, we've been listening for voices, and what we've heard is silence. Lagrange points, the invisible balancing points in space. Not everything in space is anchored to a planet or a star. Some places are held not by mass, but by math. These are the Lagrange points, 5 special positions in space where gravity and motion come together in perfect harmony. Imagine 2 objects, like the Earth and the Moon, or the Earth and the Sun, locked in orbit. Their combined gravitational pull creates a shifting field around them, but in exactly the right spots, that pull balances out. At those points, a smaller object, like a satellite, can remain almost perfectly still relative to the larger 2. No fuel, no thrust, just floating in gravitational equilibrium. There are 5 Lagrange points in any 2-body system. L1 sits between the 2 bodies, a spot where gravitational forces and orbital motion cancel each other out. The James Webb Space Telescope orbits near Earth's L2 point, just beyond Earth, always in Earth's shadow, with a clear view of deep space. L2 lies just beyond the smaller body, a perfect perch for observing the dark, cold universe without interference. L3 is on the far side of the larger E, hidden from view. like a shadow behind the sun. L4 and L5 form an equilateral triangle with the two large masses, stable zones where dust, asteroids, or even spacecraft can settle comfortably. Some of these points are stable, like gentle valleys where objects tend to stay. Others are unstable, like mountaintops, easy to balance on, but sensitive to disturbance. In fact, Jupiter's L4 and L5 points are filled with Trojan asteroids, ancient rocks that have shared its orbit for billions of years, held in place by the quiet tug of balance. Earth has Trojans too, so does Mars. These objects aren't pulled into collision or flung into space. They simply drift, held in place by invisible geometry. Lagrange points are not places you can see, but they're real. We build around them. We launch toward them. We anchor telescopes, satellites, and ideas in their stillness. So tonight, imagine space not just as motion, but as balance. Points in the void where gravity forms a silent pause, a resting place in the midst of celestial motion. We've just visited the invisible places where gravity balances and holds. But now, let's turn to something more intense. A place where gravity doesn't pause, it devours. A place long thought unseeable until we saw it. The Great Silence, what we've really heard in 60 years of SETI. In 1960, an astronomer named Frank Drake pointed a radio telescope toward two nearby stars, Tau Ceti and Epsilon Eridani. He wasn't looking for planets. He was listening for signals. It was the beginning of SETI, the search for extraterrestrial intelligence. Since then, scientists have scanned the skies, tuning into narrow frequencies where artificial signals might appear. They've searched for repeating pulses, structured broadcasts, or bursts of data that nature wouldn't produce. Over time, the technology improved, the sensitivity increased, the number of stars observed grew into the millions. And in all that time, we found nothing. Not a single confirmed message, not a single signal we can say with certainty came from an intelligent source. This absence has become known as the Great Silence. It's not just disappointing, it's puzzling. The universe is vast. There are billions of potentially habitable planets. Some are older than Earth. Life had time. Civilizations could have risen and spread. So why haven't we heard from them? Some say we're not listening long enough, that 60 years on a cosmic scale is nothing. Others suggest we're listening the wrong way. Maybe advanced civilizations use technologies we don't yet understand. Maybe they communicate with neutrinos or quantum fluctuations, not radio waves. Another possibility, they're out there, but quiet, watching, waiting, choosing not to speak. Or maybe we really are alone, not forever, but for now. A rare spark in a vast silence. There have been moments, anomalies. One of the most famous was the wow signal in 1977, a 72-second burst that looked artificial, but it never repeated. It remains unexplained, but unconfirmed. SETI continues. Projects like Breakthrough, Listen, now scan billions of radio channels across hundreds of thousands of stars. We're still listening, because even silence tells us something. It tells us the universe is quiet, that intelligence, if it exists, is not loud, not obvious, and that what we call normal may be incredibly rare. So tonight, imagine the sky not just as light, but as sound, a quiet radio field stretched across stars, and somewhere in that silence, we wait. After listening to silence among the stars, let's now turn to something louder, not in sound, but in energy. Events so bright, so violent, they outshine entire galaxies, if only for a moment. Gamma ray bursts, the brightest explosions since the Big Bang. Most of the time, space seems quiet. Stars burn, galaxies spin. But every so often, the universe erupts with a flash of light so intense, it sends radiation across billions of light years. These are gamma ray bursts, the most powerful explosions we've ever observed. They were discovered by accident in the late 1960s. US satellites designed to detect nuclear tests picked up mysterious high-energy flashes coming from space. At first, no one knew what they were. The signals were brief, lasting only seconds, but incredibly intense. Since then, we've found thousands. Some gamma ray bursts last less than 2 seconds. Others stretch longer, but all of them release more energy in a few moments than our sun will emit in its entire 10 billion year lifetime. What causes them? There are 2 main types. The first happens when massive stars die. As their cores collapse into neutron stars or black holes, the outer layers fall inward, then explode outward. If the conditions are right, the star's poles unleash focused jets of gamma radiation, thin beams that race through space at nearly the speed of light. If Earth lies in the path of one of those jets, we see the burst. The second type occurs when neutron stars collide. These dense, city-sized remnants spiral into each other, merging in a flash of destruction and creation. Along with gravitational waves, they release gamma rays, a brief signal of cosmic violence. But despite their power, gamma ray bursts are rare and distant. Most occur in galaxies far from our own. But we do wonder, what if one happened nearby? If a gamma ray burst struck Earth head-on from close range, it could damage the atmosphere, strip away protection, cause extinctions. It's one of the only cosmic events capable of sterilizing a planet, but the odds are low. We've never seen one in our galactic neighborhood. Still, we watch. Satellites like Swift and Fermi are constantly scanning the sky, waiting for the next flash. When it comes, it's over quickly. A blink, a whisper, a message from the death of something vast. So tonight, imagine the darkness above you, not still, but alive with distant energy. Somewhere, far away, a star is collapsing, a burst is coming, and for a second, the universe blinks. We've just witnessed the universe at its most violent, a flash of gamma light stretching across space. But now, let's go back to a signal that was quieter. Just once, a moment in the static that still hasn't been explained. The wow signal. One strange radio blip from deep space. On the night of August 15th, 1977, a radio telescope in Ohio quietly scanned the sky. It was part of a project called Big Ear, an early SETI experiment designed to listen for narrowband radio signals from space. Signals that nature doesn't produce. Signals that could mean something else. Most of what it detected was noise, cosmic background radiation, random bursts. But on that August evening, something different appeared. A 72-second spike, clean, focused, centered at 1420 megahertz. the exact frequency of neutral hydrogen, often considered a universal hailing frequency by SETI researchers. Astronomer Jerry Amon saw the data printed out days later, columns of letters and numbers. In the middle, one column stood out, the characters 6EQU5, a coded way of expressing signal strength. Nothing else on the page came close. He circled it in red pen and wrote just one word in the margin. Wow. That's how the signal got its name. The wow signal has never been repeated. It came from the direction of the constellation Sagittarius, near the center of the galaxy, but not from any known star. It lasted for just over a minute, then vanished. Dozens of follow-up searches have tried to find it again. No luck. What was it? Some think it was an Earth-based signal bouncing off debris. Others think it was a one-time burst from a natural object we still don't understand. But many believe it could have been artificial, a transmission from somewhere or someone far beyond. The mystery is that the signal was exactly what SETI had hoped to find. Narrowband, strong, right where it should be. But it never came again. In 2022, one study suggested a possible origin, a sun-like star about 1,800 light-years away, still unconfirmed, still uncertain. The WOW signal remains the most famous, maybe, in SETI history. A signal with no pattern, no context, and no answer. And perhaps that's what makes it so haunting. So tonight, imagine a radio dish turning slowly under the stars, a printer feeding out numbers, a single burst of something strange, and then silence. One moment, one message, one question, still echoing all these years later. From a signal that may have crossed light years, let's shift to a question. How might we send something back? Not in decades, but in centuries. Not with fuel, but with light. The heliopause, the fading edge of the solar wind. The sun doesn't just shine, it blows. Every second it releases a stream of charged particles, electrons, protons, and ions that rush outward in all directions. This stream is called the solar wind, and it fills the entire solar system. It's invisible, but it's powerful. It shapes planetary atmospheres. It creates auroras on Earth and storms on Mars. It bends magnetic fields and distorts comets into glowing tails. And it doesn't stop at the planets. The solar wind keeps going until it doesn't. Eventually, it reaches a place where it can't push any farther. A boundary, a frontier. This is the heliopause, the outer edge of the sun's influence, where the solar wind slows down and yields to the pressure of interstellar space. Beyond it, the space between stars begins. The heliopause isn't a sharp wall. It's a fading transition, a place where two winds meet. The outward flow from our sun and the incoming interstellar medium, a thin, ancient fog of particles drifting between stars. In 2012, Voyager 1 crossed this boundary. It had already traveled past all the planets, past Pluto, past the Kuiper Belt. For over 35 years, it had flown outward. Then it passed into something new. The data changed, the particle counts dropped, the magnetic field shifted, and the probe entered interstellar space, not outside the galaxy, but outside the sun's protective bubble. Voyager 2 followed in 2018. Both spacecraft are still transmitting, still drifting, and the heliopause continues to expand and contract slightly, depending on the sun's activity. Inside the heliosphere, the region shaped by the solar wind, we are shielded from some forms of cosmic radiation. It's a kind of soft barrier, not absolute, but real. Beyond it, the galaxy is different. Colder, older, less familiar. One day, perhaps, future missions will explore that space more fully. But for now, only 2 human-made objects have ever crossed the heliopause, and both are still whispering home. So tonight, imagine that edge. Not a wall, but a breath fading into silence. The last reach of the sun's wind, a boundary we barely touched, and beyond it, the stars. We've crossed the edge of the sun's domain into deep space, but even out there among distant stars, we've begun to find something remarkable. Worlds with skies of their own. The light sail concept. Traveling with nothing but sunlight, space is vast. Rockets are powerful, but even they struggle with distance. Fuel runs out, speed fades. But what if we could travel without fuel at all? That's the idea behind a light sail, a spacecraft pushed not by engines, but by sunlight. It sounds like science fiction, but the physics is real. Light carries momentum, not much, but enough. When photons, the tiny packets of light, hit a reflective surface, they exert a small push. Multiply that push across a large, ultra-thin surface, and you get acceleration. Tiny at first, but constant. In space, where there's no friction, even a slow, steady push can become fast over time. A light sail works like a solar sailboat, catching the stream of sunlight instead of wind. It doesn't need fuel. It just needs a giant, lightweight surface, often made of reflective material like mylar or captain, and enough time. The concept has been tested. In 2010, Japan launched Ikaros, the first interplanetary solar sail. It unfurled its sails in space and successfully used sunlight to change its trajectory. In 2019, the Planetary Society's LightSail 2 mission demonstrated controlled flight using solar pressure, orbiting Earth with nothing but photons. But the dream goes farther. Some scientists and engineers are working on laser-driven light sails, where powerful ground-based lasers would beam focused energy at the sail, pushing it to enormous speeds. A project called Breakthrough Starshot aims to send tiny probes to Alpha Centauri, our nearest star system, within a human lifetime. To do that, they'd need to accelerate a sail to 20% the speed of light, reaching another star in just over 20 years. The spacecraft would be gram-sized, but the speed, unimaginable. Challenges remain. Controlling the sail, surviving interstellar dust, communicating across light years. But the core idea is simple. Let light do the work. No rockets, no fuel tanks, just mirrors and momentum. So tonight, imagine a thin silver sheet floating silently in space. No flame, no noise. Just sunlight pressing gently against it. Day after day, year after year, until it drifts between stars. A sail for the darkness. From sails drifting on sunlight, let's follow the wind itself. Not the kind you feel on Earth, but something much older, much larger. A wind that comes from the sun and eventually fades into silence. Alien atmospheres. What we found on distant exoplanets. When astronomers first discovered planets beyond our solar system, exoplanets, they found gas giants, Hot, massive, fast orbiting. Too far away to study in detail. Just faint dips of starlight. Hints, but technology moved forward. And now, not only can we detect those worlds, we can begin to study their atmospheres. Not by visiting them, not by flying through their clouds, but by watching the way their starlight changes as the planets pass in front of their stars, a method called transit spectroscopy. When a planet crosses its star, some of the starlight filters through the planet's atmosphere. Molecules in that atmosphere absorb specific wavelengths of light, creating a kind of fingerprint. From Earth or from orbiting telescopes, we can read that fingerprint. And what we've found is astonishing. Some exoplanets have clouds of glass, literally silicates suspended in superheated skies. Others have iron rain, falling through thick, dark atmospheres. One planet, HD 19733b, appears deep blue from space, not because of oceans, but because of light scattering through violent winds and tiny particles. Some atmospheres are rich in hydrogen and helium, like Jupiter. Others contain sodium, potassium, even water vapor. In 2019, researchers detected water in the atmosphere of K218b, a super-Earth in its star's habitable zone. Does that mean it's habitable? Not yet, but it's a beginning. We've also found carbon dioxide on gas giants, methane, ammonia. These elements tell us about pressure, temperature, chemistry, and sometimes even about the structure beneath. The James Webb Space Telescope is now transforming this work. Its infrared sensitivity allows it to peer deeper into distant skies. Already, it is refining our understanding of planets light years away, measuring the height of clouds, the depth of storms, the shape of heat. And one day, it may find something more, a chemical imbalance, a pattern that looks unnatural, a trace of something living. But even now, what we've seen is more than we ever imagined. So tonight, imagine a planet far away, not rocky, not reachable, but with air of its own, skies that shimmer with exotic storms, and clouds that hide a world still waiting to be understood. From skies on distant worlds, let's turn now to something even less tangible, a question older than science itself, a dream, and a paradox. Could we ever move through time, not just forward, but backward? Could time travel be possible? According to physics, time feels like a river, always flowing forward. Seconds pass, days end, memories build. We move through time the way we move through space, but only in one direction. Still, physicists have asked, is that limit real? Or is it just how we experience time? According to Einstein's theory of relativity, time and space are part of the same fabric. Space-time. Massive objects, like stars or black holes, curve that fabric. And the more extreme the curve, the more time itself can slow. This isn't theory, it's been measured. Astronauts on the International Space Station experience time slightly differently than people on Earth. Clocks tick faster or slower depending on gravity and speed. This is called time dilation, and it means, in a sense, time travel forward is already possible, just very slight. But what about going backward? That's harder. Some solutions to Einstein's equations suggest the existence of closed time-like curves, paths through space-time that loop back on themselves. If such paths could exist, an object might return to its own past. One famous idea is the wormhole, a tunnel through space-time. In theory, if one end of a wormhole were moved close to a massive object or accelerated to near light speed, time at that end would slow relative to the other. Re-entering the wormhole could place you at an earlier time, on the other side. But these ideas come with enormous problems. Wormholes may not be stable. Exotic matter would be needed to keep them open, a form of matter that hasn't been proven to exist. And even if they were possible, paradoxes emerge. What happens if you prevent your own journey? Could the universe allow events to undo themselves? Many physicists believe nature has mechanisms, still unknown, that prevent such contradictions. Others suggest that if backward time travel is ever possible, it must follow a rule: self-consistency. You can't change the past. You were always part of it. Still, others wonder whether time travel might lead not to your past, but to a different one, a branch of time, a parallel timeline. For now, it remains imagination, grounded in equations, constrained by reality, but never fully ruled out. So tonight, as the seconds pass softly around you, think of time not as a line, but as a landscape, one we walk through, one we bend slightly, and maybe, one day, one will travel more freely than we ever thought possible. The dark flow is something pulling our universe from beyond. When we look into the cosmos, we expect to see movement, galaxies expanding away from each other, nebulas drifting, clusters separating as the universe continues to grow. But in 2008, scientists found something they didn't expect. Using data from NASA's Wilkinson Microwave Anisotropy Probe, WMAP, researchers observed the motion of galaxy clusters on a vast scale. These clusters weren't just following the normal expansion. They were all drifting in the same direction. It wasn't random. It wasn't chaotic. It was as if something far beyond the observable universe was pulling on them. A gentle tug, a motion outside the script of standard cosmology. This mysterious movement was named the dark flow. It's not dark because of color or light, but because we don't know what causes it. And unlike dark matter or dark energy, which are embedded in current cosmological models, dark flow doesn't have a clear place in what we thought we understood. The clusters appeared to be moving toward a specific patch of sky, near the constellations Centaurus and Vela, at speeds of up to 600 million kilometers per hour. But what could cause such motion? Some theorists proposed a structure outside our visible universe, perhaps a massive collection of matter that we simply can't see beyond the cosmic horizon. Others have suggested it might be a sign of another universe entirely, one brushing against ours, or maybe a leftover ripple from events before the Big Bang. Still, the data remains controversial. Later missions like Planck didn't confirm the flow with the same clarity. Some argue it was an artifact of analysis. Others say it's still there, just harder to measure now. But the idea, the possibility, has stayed. Because if true, dark flow means we are being influenced by something we can never see, something outside the map, beyond the edge. So tonight, as you close your eyes and imagine galaxies adrift, think of the great cosmic rivers pulling us silently, not just in space, but perhaps toward a greater mystery. Wherever that current leads, It may already be shaping everything we know. If something is pulling us from beyond, what might be stirring much closer to home, beneath the toxic clouds of a familiar planet. Let's shift now to a world that glows in twilight skies and holds a secret high in its atmosphere. Venus has phosphine. Could that mean life in the clouds? Venus is not a place where we expect to find life. Its surface is a furnace, hotter than Mercury, despite being farther from the sun. The air is thick with carbon dioxide. Clouds of sulfuric acid swirl endlessly. The pressure on the ground is crushing, more than 90 times that of Earth. But high above that hellish surface, something strange was found. In 2020, a team of scientists announced they had detected traces of a gas called phosphine floating in Venus's upper cloud layer, a region where the temperature is milder, where sunlight filters through, and where conditions, while harsh, are not entirely alien to Earth's upper atmosphere. And that detection stirred the imagination of scientists everywhere. Why? Because phosphine is a chemical that, on Earth, is almost entirely associated with life. It can be produced industrially, yes, but in nature, it's created by anaerobic organisms, microbes that live in low oxygen environments like swamps or deep underground. So to find it on another planet, especially on Venus, raised a tantalizing possibility. Could there be microbial life floating in its clouds? The idea isn't new. As far back as the 1960s, scientists speculated that if Venus once had oceans, and if life evolved before the planet transformed into a runaway greenhouse, some forms of life might have adapted, retreating into the upper atmosphere. Tiny, resistant, suspended in droplets, living in a perpetual sky. But the phosphine detection is controversial. Other scientists questioned the data. The signal could have been confused with sulfur dioxide. Reanalyses have produced conflicting results. Some confirm it, others do not. And even if the detection holds, phosphine can, in theory, be produced abiotically by geological or chemical processes we don't fully understand yet. Still, the mystery remains. A signal in the sky, a whisper from a planet we thought was long dead. NASA and other agencies are now planning new missions to Venus. The Da Vinci Plus and Veritas probes will explore its atmosphere and geology with unprecedented precision. And maybe, just maybe, they'll answer a question we've barely dared to ask. Could life survive in a place we once wrote off entirely? From the golden light of Venus to the deepest reaches of the radio sky, we now follow a shape, not a planet, not a star, but a whispering X in the void, a celestial mark unlike anything else. What happens when two black holes collide? Black holes are often imagined as solitary beasts, devouring stars, bending time, lurking in darkness. But space is rarely still, and when galaxies drift together, their black holes do too, slowly, relentlessly, and sometimes they collide. For decades, this was theory, a distant event too quiet, too slow to be heard. But that changed in 2015 when the LIGO Observatory recorded something that had never been directly observed before. Gravitational waves, ripples in space-time itself, and they were coming from the final seconds of a black hole merger. Two black holes, one about 36 times the mass of the Sun, the other 29, had been spiraling around each other for millions of years. With every orbit, They shed energy, drawing closer and closer until at last they merged. In a fraction of a second, they formed a new black hole, heavier than either, but not as massive as the sum, because some of their mass, about 3 suns worth, had been turned into energy, not light, not heat, but a tremor through the universe, a wave of gravity itself, moving outward at the speed of light. The detectors on Earth stretched and squeezed, not by much, less than a fraction of a proton's width, but enough to be measured. And so, we finally heard black holes collide. It wasn't a crash, not like planets or stars. There was no explosion, no burst of light, just gravity, singing. Since then, dozens more mergers have been recorded, some from black holes over 80 solar masses, some involving neutron stars, some still unexplained. Together, they've opened a new branch of astronomy, gravitational wave astronomy, a way of listening to the cosmos. And yet, many questions remain. How do such massive black holes form? What happens in the chaotic moment of collision? Could such events create new kinds of matter? Do they leave behind kicks, violent recoils that launch the resulting black hole away? And what does this tell us about the structure of space itself? As you rest, imagine 2 invisible giants locked in a dance so tight, so perfect, that even the universe has no choice but to ripple. It is silent, it is final, and it is beautiful. From the shuddering echoes of colliding giants, let's shift our gaze to a quieter promise, a star not too far from us, dim but steady, where something extraordinary orbits in silence. The radio galaxy that looks like a ghostly X. Most galaxies look like graceful spirals or glowing ellipses, great wheels of stars drifting in space. But sometimes, through radio telescopes, we see something stranger. In the constellation of Cetus, nearly 800 million light years away, lies a galaxy known not for how it shines, but for how it stretches. Its name is 3C223.1, a radio galaxy with lobes so large they don't even appear in visible light. But when astronomers mapped its radio emissions, they saw something unexpected. A perfect X. 2 great arms of radio jets shoot out horizontally, but another, fainter pair, almost perpendicular, extends in a different direction. Together they form a cross in the sky, faint, symmetrical, and haunting. But what causes this? Radio galaxies are powered by supermassive black holes at their centers, giants millions or even billions of times the mass of our sun. As matter spirals into them, intense energy is released, often shooting out as jets of charged particles, traveling near the speed of light. In most cases, these jets are aligned in one direction, forming twin lobes. But in 3C223.1 and a few others like it, we see 2 sets of lobes, oriented at very different angles. The leading theory: the central black hole changed its axis. Astronomers think this galaxy may have gone through a cosmic merger. Perhaps another black hole spiraled in after a collision with another galaxy, twisting the spin of the central engine. The old jets faded, and new ones erupted in a new direction, leaving behind a glowing memory of that shift. The result is not chaos, but something eerily balanced. A fossil of motion, a signature of transformation. Others suggest that the X shape might come from backflowing material, as plasma bends and spreads through magnetic fields, or from ancient structures in the galaxy's environment that shaped the jets over time. Whatever the case, these radio galaxies are not just curiosities. They're cosmic signatures of violence and time, and their eerie symmetry speaks to something deep, that even in the most powerful upheavals, space leaves behind beauty. So now, as you drift into rest, imagine a galaxy painting a silent X across the stars, not to mark a treasure, but to remind us that even black holes leave behind their brushstrokes. That ghostly X in the sky marks a memory of motion, a change in direction. But what happens when the forces behind those jets don't just shift, but meet? The TRAPPIST-1 system, 7 Earth-sized worlds in one place. In 2017, the astronomical community paused. A discovery was announced that seemed like science fiction. A single star orbited by 7 rocky planets, all roughly the size of Earth. This star is called TRAPPIST-1. It's a red dwarf, much cooler and smaller than our Sun, just 9% of its mass. It's faint, invisible to the naked eye, and yet in its gentle orbit lies the most Earth-like planetary system we've ever found. 7 worlds, all terrestrial, some warm enough possibly for liquid water. The system lies about 40 light-years away, in the constellation Aquarius. In cosmic terms, that's close. A neighbor. 3 of the planets orbit in what's called the habitable zone, the region around a star where temperatures might allow water to exist on the surface. But TRAPPIST-1 is so dim that even its inner planets receive soft red light, like permanent twilight. They orbit close, extremely close, with years that last just a few Earth days. But because the star is so small, that tight proximity doesn't bake them. Instead, it creates a compact, clockwork system, so balanced that some planets gravitationally tug on each other, creating measurable wobbles, a kind of cosmic resonance. Astronomers believe that some of these planets could have atmospheres, some might have oceans, others might be too hot or too cold, but all are rocky, all are real. And for the first time, we weren't talking about a single Earth-like world. We were talking about 7. The discovery reshaped how we think about planetary systems. Around small stars, there might be countless Earth-sized worlds, huddled close, orbiting slowly burning suns. And TRAPPIST-1 is just the beginning. Future telescopes, like the James Webb Space Telescope, have already begun studying these planets' atmospheres, searching for traces of water or even biosignatures. We don't know what we'll find, but in the dim glow of a quiet star, far away 7 rocky worlds circle in near-perfect harmony. A cosmic family, a symphony of planets. So tonight, as you drift into sleep, imagine the TRAPPIST-1 system not as distant science, but as a real place where Earth-sized worlds dance to a rhythm older than memory. If TRAPPIST-1 shows us worlds we can imagine, the next mystery reveals something we cannot see, but which shapes everything. Let's follow the traces of a cosmic collision that gave us a glimpse into the invisible. The moon's origin. Was it born from a giant impact? The moon has always felt like a constant. It pulls our tides. It lights the night. It inspired calendars, stories, and songs long before we understood what it was. But where did it come from? Of all the bodies in the solar system, the moon is unusually large compared to its planet. It's over a quarter the width of Earth. Its presence is too significant to be an afterthought. For centuries, there were theories that it formed alongside Earth, that it was captured, or even that it was spun off from Earth's surface like molten spray. But today, the leading explanation is something far more violent. It's called the giant impact hypothesis. According to this theory, about 4.5 billion years ago, a Mars-sized body, often referred to as Theia, collided with the young Earth. The impact was catastrophic. The early planet was struck at an angle, throwing molten rock and debris high into space. Some of that debris re-entered Earth. Some escaped entirely. And some, over days, weeks, maybe months, began to coalesce in orbit. Gravity took over. The fragments circled, collided, and fused, until eventually, the Moon was born. Evidence for this theory is compelling. Moon rocks brought back by the Apollo missions share many chemical similarities with Earth's mantle, suggesting they came from a common origin. But they're also slightly different, hinting at the presence of another body, like Theia. Computer simulations show that such an impact could create a stable moon with the orbit and size we see today. And this event might explain why Earth ended up with a tilted axis, giving us seasons, and why the moon is slowly drifting away even now. But mysteries remain. What happened to Theia? Was it destroyed entirely? Or is some part of it buried deep within Earth or the moon? And why do some isotopic signatures match Earth so precisely, as if Theia never really existed at all? The giant impact hypothesis isn't just a theory about destruction. It's a story of creation, a moment where chaos gave rise to the companion that has followed us ever since. So, tonight, as you sleep under its silver glow, remember, the moon may be a child of fire, born from a collision that changed everything. If the moon was born in silence, the space between worlds seems even quieter. But silence in space is not absence. Sometimes it's waiting to be translated. Let's now drift into a question not of light, but of sound. The bullet cluster, proof that dark matter might be real. There are times in science when something invisible becomes undeniable. For decades, astronomers have suspected that most of the mass in the universe isn't made of stars, planets, or gas. It's something else, something that doesn't shine, doesn't absorb, and doesn't interact with light. They called it dark matter. We can't see it, we can't touch it, but galaxies rotate too fast for their visible matter to hold them together. Clusters of galaxies move in ways that ordinary gravity can't explain. Light bends around invisible shapes. Still, until the mid-2000s, the case for dark matter was indirect. Theorized, modeled, but not seen. Then came the bullet cluster. Two galaxy clusters, massive collections of galaxies, stars, and hot gas, collided over hundreds of millions of years. The result is a violent, complex structure about 3.8 billion light-years away in the constellation Carina. Here's what happened. When the clusters passed through each other, their stars, being tiny compared to the distances between them, mostly slipped past without collision. But the hot gas in each cluster, which makes up most of their visible mass, collided violently, slowing down and heating up. This gas glows in X-rays, and we can map it. But when scientists used gravitational lensing, the bending of light from background galaxies, to trace the total mass of the system, something stunning appeared. The bulk of the mass wasn't with the hot gas. It had moved ahead. It was separated from the normal matter. The lensing showed that the invisible mass, presumed to be dark matter, had passed through without resistance, unaffected, detached from everything we can see. This was more than just a theory. It was visual, measurable evidence that some form of non-interacting mass exists, something that doesn't collide, that doesn't glow, but that shapes gravity on a cosmic scale. The bullet cluster became a keystone, a cosmic crime scene, a snapshot of the invisible moving through the visible. We still don't know what dark matter is. It might be particles, it might be fields, it might be something we've never imagined. But because of this cluster, we know it's there. So tonight, as your thoughts soften and float, picture two galaxy clusters crashing in silence, and the ghostly shadow that kept on going. From distant clusters to something far more familiar, let's now turn our gaze homeward, to a presence that has lit our night skies for all of human memory. But where did it come from? And how did it become ours? The sound of the solar wind, how we turned plasma into music. In the vacuum of space, there is no air, no wind rustling leaves, no waves crashing, no footsteps on gravel. Sound, as we know it, pressure waves moving through air, cannot travel where there is no medium. That's why space is so often described as silent. But that silence is deceptive, because space is full of plasma, a state of matter where gas becomes charged, creating vast flows of energetic particles, and the sun is constantly pouring this plasma out into the solar system. We call it the solar wind. It's not wind in the earthly sense. There's no breeze you could feel. But this stream of particles, electrons and protons, moves fast. It shapes the magnetic fields of planets, creates auroras near Earth's poles, and even defines the very edge of our solar system in a bubble called the heliosphere. And though you can't hear it with your ears, you can convert its data into sound using spacecraft like Parker Solar Probe, Voyager, and Cluster. Scientists collect measurements of plasma density, magnetic activity, and particle motion. These numbers, frequencies, amplitudes, oscillations, can be translated into sound. It's called data sonification, and when applied to the solar wind, the result is eerie and beautiful. A low, wavering hum, sudden whooshes as bursts of particles stream past, crackles and warbles as magnetic fields twist and ripple. It sounds like a storm in slow motion. It sounds like the sun breathing. These aren't sounds in the traditional sense, but rather audible interpretations of physical forces. They let us listen to space not as a vacuum, but as a dynamic, shifting sea of energy. For scientists, sonification helps identify patterns, anomalies, and bursts of activity. For the rest of us, it offers something more emotional, a bridge between numbers and experience, a way to feel what's otherwise invisible. So now, as you settle deeper into stillness, imagine the solar wind streaming past you, soft, constant, and unseen. And in that current, imagine the quiet music of the sun, not glowing, but whispering across the darkness, in waves you cannot hear unless you choose to listen. If the sun sings through solar wind, imagine hearing not one voice in the sky, but three. Let's now explore a world that orbits beneath a trio of suns and ask, how could anything hold together under such a dance? A planet with 3 suns. How stable is that? We're used to the idea of one star, one system. A planet orbiting a sun, with perhaps moons or rings, seasons and tides. But the universe, as always, writes stranger scripts. In 2016, astronomers confirmed the discovery of a planet named HD 131399AB, orbiting within a triple star system, roughly 320 light-years away in the constellation Centaurus. It became known as the planet with 3 suns. Picture this. On this world, a gas giant, perhaps twice the size of Jupiter, the sky is never truly dark. One sun rises and falls. Another might hover on the horizon. A third could paint long shadows, even at what should be night. The stars orbit each other in a complex ballet. At the center are 2 stars tightly bound in a binary orbit. The third star, farther out, moves more slowly, and the planet itself orbits in a wide, sweeping path that encompasses all 3. How does that work? Very carefully. For a planet to survive in a multi-star system, its orbit must find a balance. Too close to one star, and it might be torn away by the others. Too far, and it risks being ejected from the system entirely. Early models questioned the stability of HD 131399AB's orbit. Some simulations showed it could be unstable over millions of years, prone to being flung into deep space. Others suggested it might be more stable than expected, depending on the exact tilt and distance. Still, even if it's temporary in cosmic terms, the very existence of such a world challenges our understanding of what planetary systems can be. Could such planets host moons? Could light from 3 stars create wild, shifting climates? Could life exist under such complicated rhythms? Or is this world a lonely drifter, bathing in golden light, its days and nights a slow swirl of shadows? HD 131398 may not be unique. Other planets have been found in binary systems, but to orbit 3 suns and to survive is to thread a needle across gravitational chaos. So as you rest, picture a gas giant beneath 3 stars, drifting through a sky where dusk never ends, and wonder what it feels like to have not 1 sun, but 3, and yet no true night. If 3 suns make the sky endlessly bright, what then of the places where there are no stars at all? Let's drift now toward one of the quietest, loneliest regions in the known universe. Mars has blue sunsets. Here's why we know Mars by its color. The red planet, a world of rust-colored dust, ochre plains, and copper hills. Its surface, bathed in iron oxide, reflects sunlight in a warm, reddish hue. But on Mars, something unexpected happens when the day ends. The sky turns blue. It's the opposite of Earth. Here, our skies are blue during the day and red at sunset. But on Mars, it's reversed. As the sun dips below the horizon, the Martian sky deepens into a cool, twilight blue. Why? It all comes down to atmosphere and dust. Mars has a thin atmosphere, just 1% the pressure of Earth's, but it's filled with fine dust particles suspended in the air. These particles don't scatter light in the same way our nitrogen and oxygen-rich atmosphere does. On Earth, short blue wavelengths of sunlight get scattered in all directions by our dense air. That's why our sky is blue. At sunset, when the sun is low, its light has to travel through more atmosphere, and the blue gets scattered away, leaving us with rich reds and oranges. On Mars, things work differently. The fine Martian dust scatters red light away from the line of sight, but it lets blue light pass through more directly. At sunset, this effect becomes strongest. The result: a small concentrated blue glow near the setting sun, surrounded by an amber sky. It's not a broad, bright blue like Earth's daytime sky. It's subtle, soft, almost ghostly. Rovers like Spirit, Opportunity, Curiosity, and Perseverance have all captured these moments. Blue sunsets over alien terrain. The images feel surreal, not because they're unfamiliar, but because they almost seem familiar, just inverted. It's a reminder that even basic phenomena like color and light are shaped entirely by environment. And perhaps more beautifully, it's a sign that other skies, on other worlds, will surprise us. They won't look like ours, but they'll be no less poetic. So tonight, as you ease into sleep, imagine sitting on a Martian hill, wrapped against the cold and watching the sky fade from gold to sapphire as the last light of day retreats into a blue that belongs only to Mars. We've traveled across galaxies, through voids and sunsets on other worlds, but what if the strangest, most spacious place of all is inside you? The Boötes Void, the giant hole in the universe. Imagine pointing a telescope at the night sky and seeing almost nothing, not just a patch of darkness between stars, but a place where there are no stars, no galaxies, no glowing nebulae, not for hundreds of millions of light years. This is the Boötes Void, discovered in 1981 by astronomer Robert Kirshner and his team. This enormous region lies in the direction of the constellation Boötes. It's not just large, it's staggering. Roughly 330 million light-years across, the Boötes Void is one of the largest known structures, or rather non-structures, in the observable universe. To grasp its scale, if the Milky Way galaxy were the size of a grain of sand, the Boötes Void would be a cavern the size of a cathedral. Inside it, there are galaxies, but only a few. Where we'd normally expect thousands, there are barely a couple of dozen. It's as if the universe simply forgot to fill that space. So what causes such a void? The early universe wasn't uniform. After the Big Bang, matter clumped together under gravity, forming filaments, vast cosmic threads of galaxies. And between them, empty pockets. The Boötes Void is one such pocket, an area where density fluctuations left behind a region with little matter. Over billions of years, it stayed sparse, while other areas bloomed with stars and galaxies. But even by cosmic standards, the Boötes Void is unusually empty. Some have speculated it might be the result of multiple smaller voids merging, forming a supervoid. Others wondered whether it's a statistical outlier, just an especially extreme dip in density. A few fringe theories even invoked alien civilizations, using the void as a marker or a byproduct of advanced activity. But mainstream science remains grounded. The void is real, and its silence speaks to how structure formed in the cosmos. Looking at the Boötes Void is like peering into the breath of the universe. A pause, a stillness. Not every part of the cosmos is crowded. Some regions are vast, cold, and almost entirely dark. And in that darkness, we're reminded that emptiness too has meaning. So as your thoughts grow lighter, picture this: a hole in the sky so large that entire galaxies drift inside it like dust. A cosmic silence that holds without echo across hundreds of millions of light years. From a vast void between galaxies, let's now return to a familiar world, one we visited many times in our imagination. But tonight, we're not focused on its red dust. We're waiting for sunset. The space between atoms. Most of you is empty. You're made of matter. Atoms, countless trillions of them, arranged in patterns to build your bones, your blood, your breath. It feels solid, real. Your hand, resting gently, seems like something definite. But that feeling is an illusion, because most of you is empty space. Let's look closer. An atom is made of a nucleus, protons and neutrons, surrounded by a cloud of electrons. The nucleus sits at the center, incredibly dense, while electrons orbit at relatively vast distances. If an atom were the size of a cathedral, the nucleus would be a grain of rice at its center, and the electrons would orbit near the outer walls. Everything in between, empty. The space between the nucleus and the electrons makes up 99% of the atom's volume. And this isn't just about atoms being small, it's about scale. That space isn't filled with air or particles. It's truly, profoundly, nothing. So how do we feel solid? Why don't our hands pass through each other? The answer lies in electromagnetic forces. When you touch something, the electrons in your atoms repel the electrons in what you're touching. You're not really touching in the classical sense. You're hovering near, feeling resistance from quantum forces. Matter resists collapse because of quantum mechanics, specifically the Pauli exclusion principle, which keeps electrons from occupying the same state. In a way, you're held together by rules, not by mass. Even the protons and neutrons inside the nucleus are made of quarks, and those two are surrounded by space and force fields. So if most of every atom is empty, and you are made of atoms, you are mostly empty space. And yet, here you are, breathing, thinking, resting, held together not by density, but by balance. It's strange, isn't it? To be both something and almost nothing at once. To be made of space and still feel full. So as you settle into stillness tonight, imagine drifting not through stars, but through the space between them. The same kind of space that lives within you. Quiet, vast, and beautifully structured. You are not just in the universe, you are built like it. From the space within you to the storms far beyond, let's now drift toward a giant, a planet of gas, color, and motion. And on its surface, a storm that simply refuses to end. The Great Red Spot, a storm that's older than our telescopes. Jupiter is a world of extremes. It's the largest planet in our solar system, a gas giant with no solid surface, just layer upon layer of swirling atmosphere. It rotates faster than any other planet, once every 10 hours, creating powerful weather systems that stretch across thousands of kilometers. And within this chaos sits one of the most iconic features in planetary science, the Great Red Spot. It's a storm, a vast spinning oval, more than twice the width of Earth, raging in Jupiter's southern hemisphere. It's an anticyclone, meaning it rotates counter to the planet's overall spin, with winds reaching up to 430 kilometers per hour. We've seen hurricanes on Earth that last a week, maybe two, but this one, it's been going for at least 350 years. The first telescopic observations of the Great Red Spot date back to the 1600s, and it was already massive then. Over time, it's changed, shrinking, fading in color, fluctuating in shape, but it hasn't stopped. It's a storm without rest. What fuels it? Jupiter's atmosphere is made of hydrogen, helium, and trace compounds like ammonia and methane. The planet has no ground to slow storms down, just endless fluid motion. Warmth from its interior helps drive convection, and Jupiter's fast rotation stretches storms into bands and ovals. The red spot sits between two powerful jet streams that help stabilize it, like a ball caught between conveyor belts moving in opposite directions. Still, it's shrinking. In the last century, it has diminished dramatically, from about 40,000 kilometers across to under 15,000. Some scientists wonder if it might disappear within our lifetime. Others believe it could persist in another form, smaller but still potent. And despite centuries of observation, we still don't know why it's red. Theories point to chemical reactions caused by ultraviolet sunlight or trace compounds dredged up from deeper layers. But the truth is, we don't fully understand it. A storm older than our technology, older than the United States, older than the modern world, still spinning, still defying time. So as you relax tonight, imagine floating above Jupiter's clouds, watching the red spot turn. Vast, ancient, and tireless, a whispering vortex on a world of gas. From Jupiter's ceaseless storm, let's now move outward, past the known planets, beyond the cold breath of Neptune. There lies a frontier, not empty, but filled with ancient relics. Titan has lakes, but they're not what you think when you hear the word lakes. You probably picture water, still, glassy surfaces, ripples on a summer shore, maybe mountain reflections. But on Titan, Saturn's largest moon, lakes mean something else entirely. Titan is the only place in the solar system, besides Earth, known to have stable liquids on its surface. But they're not lakes of water. They're made of liquid methane and ethane, hydrocarbons that would be gases on Earth, but flow like water in Titan's frigid climate. Temperatures on Titan hover around 179 degrees Celsius. At that point, methane behaves like water does here, forming clouds, falling as rain, carving rivers, pooling into lakes and seas. In fact, Titan has a full hydrological cycle, just not with H2O. It rains, it evaporates, it flows. The result? A world eerily Earth-like in landscape, but utterly alien in chemistry. The northern polar region is home to vast methane seas, like Kraken Mare, which spans hundreds of kilometers. Radar from NASA's Cassini spacecraft has mapped its shoreline, revealing peninsulas, islands, and possibly even waves. Smaller lakes dot the terrain, smooth, dark features that reflect radar-like glass. Some are filled, others appear mysteriously empty, as if drained. Some may be seasonal, and Titan's skies, thick with orange haze, a nitrogen-rich atmosphere even denser than Earth's. Light filters through like dusk, casting long shadows over ridged plains and dune fields made of frozen organic particles. Despite the cold, Titan may be one of the most dynamic places in the solar system, its surface changes, its weather shifts, its rivers meander and etch the land. Beneath that surface, it's believed there's a subterranean ocean of liquid water, possibly salty, possibly harboring conditions for life. Some scientists dream of sending a floating probe, a drone boat, to sail across Kraken Mare, to listen for waves, to drift among alien shores. So as you rest, imagine walking along a shore where the water is cold methane, the air is thick, the horizon fades into orange fog, and the sky above Saturn glows faintly behind the clouds. Stillness, reflection, and a world where lakes tell a different story. From the methane lakes of a distant moon, we now lift off into open space, propelled not by fire or fuel, but by something far gentler, something that touches your skin every day and can move a ship through the stars. The Kuiper Belt, our solar system's forgotten frontier. Most of us think of the solar system as ending with Neptune, but it doesn't. Beyond that ice giant, starting around 30 astronomical units from the Sun, begins a wide, cold expanse known as the Kuiper Belt, a massive ring of icy bodies, dwarf planets, and remnants from the solar system's early days. It's like the asteroid belt, but far larger and colder. The Kuiper Belt extends out to nearly 50 AU, about 7.5 billion kilometers, and is filled with billions of objects, frozen fragments of water, methane, and ammonia. These aren't planets or moons, but leftovers, building blocks that never coalesced. And one of those leftovers became famous: Pluto. When Pluto was discovered in 1930, it was considered the 9th planet. But over time, astronomers found more Pluto-like objects in similar orbits, some nearly the same size. It became clear that Pluto wasn't alone. It was part of a population. The Kuiper Belt is where Pluto lives, along with other dwarf planets like Eris, Haumea, and Makemake. These worlds are icy, distant, and mysterious, some with thin atmospheres, others with moons or spinning so fast they become egg-shaped. And then there are the cold classicals, objects that have remained untouched, on stable orbits since the birth of the solar system. They may hold clues to how planets formed, how water arrived on Earth, or what the early solar environment was like. We've only visited the Kuiper Belt once. In 2015, NASA's New Horizons mission flew past Pluto, revealing mountains of ice, smooth plains of nitrogen, and a heart-shaped feature that captured imaginations everywhere. Later, it visited another Kuiper Belt object, Arakoth, a contact binary shaped like a peanut, untouched for billions of years. The Kuiper Belt is still largely unexplored. Most of its members are tiny, far too faint for even our best telescopes. But what lies beyond it? Perhaps the Oort cloud, perhaps Planet 9, perhaps silence. But for now, the Kuiper Belt marks a border, not just of space, but of understanding. So as your breath slows, imagine drifting through that cold outer ring, past the orbits of known giants, among ancient ice, silent witnesses to the sun's earliest days, still circling in the dark. After drifting through frozen rings and silent relics, let's turn to something more unexpected. Not what space looks like, but what it might smell like. The space smells like burnt metal, the chemistry of the void. You've probably heard it before. Space has no air. There's no atmosphere to carry scent, no wind to bring aromas. In the vacuum, molecules don't flow across your nose. And yet, astronauts returning from spacewalks have described a distinct smell, not in space itself, but on their suits, on equipment, in the airlocks once they re-enter the station, a scent that lingers. What do they say it smells like? Burned metal, welding fumes, charred steak, ozone, gunpowder, a strange, acrid metallic aroma that's hard to place and impossible to forget. But how can that be? The answer lies in chemistry. When astronauts go on extravehicular activity, a spacewalk, their suits and tools are exposed to the harsh conditions of space. Radiation, micrometeoroids, solar particles, and most importantly, atomic oxygen. Atomic oxygen is different from the O2 we breathe. It's a single oxygen atom, highly reactive, and found in low Earth orbit. It's created when sunlight splits O2 molecules apart, and it's known to corrode spacecraft surfaces. When equipment is brought back into the station, this reactive atomic oxygen interacts with the air inside, triggering chemical reactions that release volatile molecules. What astronauts smell isn't space itself, but the byproducts of space exposure. The surfaces of the suit or tools may have picked up traces of polycyclic aromatic hydrocarbons, PAHs, compounds formed by high-energy interactions, similar to what's created during combustion. These PAHs have strong, metallic, burnt-like odors. The same family of molecules gives grilled meat its smoky flavor and welding its signature scent. So, in a way, the smell of space is a footprint, an echo of chemical violence translated into a scent. NASA even worked with scent designers to recreate the aroma for training purposes, helping astronauts acclimate. It's a detail we rarely think about. We imagine space as visual, stars, planets, galaxies, but it also leaves a trace, one that lingers in the air, sharp and unforgettable. So as your senses soften, imagine floating back into the airlock, taking off your helmet, and catching a sudden breath of something unexpected. A chemical whisper from the void, not sweet, not fragrant, but very real. We've caught the scent of the void. Now let's descend, not onto a planet, but onto a moon, one that echoes with rain, rivers, and lakes, but none of it made of water. Solar sails, sailing the light of the sun in the age of wooden ships and canvas sails. The oceans were conquered by wind. Now, centuries later, we've discovered another kind of sail, one not pushed by air, but by sunlight. Light, though it seems weightless, carries momentum. Photons, tiny particles of light, exert pressure when they strike a surface. It's minuscule, but in the vacuum of space, with no air resistance and enough time, that pressure can build up, accelerating an object to astonishing speeds. This is the principle behind solar sails. They are spacecraft with large, thin, reflective sails, sometimes the size of a tennis court or larger, designed to catch the sun's photons, not to burn, but to push. No fuel, no engines, just sunlight and time. The idea sounds like science fiction. In fact, it has been. Arthur C. Clarke wrote about it. Carl Sagan championed it. And today, solar sails are very real. In 2010, Japan's Ikaros mission became the first to successfully deploy a solar sail in interplanetary space. It proved the concept worked, using sunlight alone to adjust course and orientation. Later, the light sail missions, led by the Planetary Society, continued testing. These missions showed how small, lightweight satellites could maneuver using only the sun. Solar sails aren't fast at first, but their acceleration is continuous. Unlike chemical rockets that burn out after minutes or hours, a solar sail keeps gaining speed day after day. Over time, it could surpass even the fastest spacecraft. Some future missions dream even bigger, using lasers from Earth or space to push sails toward distant stars. Concepts like Breakthrough Starshot imagine sending gram-scale probes to Proxima Centauri, reaching 20% the speed of light. There are challenges: deploying vast, delicate sails, navigating solar storms, pointing with precision across billions of kilometers. But the vision is simple, elegant, a spacecraft gleaming and silent, catching sunlight like wind, sailing through space with no engine noise, no fuel trail, only photons dancing off mirrored fabric. So as you breathe quietly tonight, imagine drifting on a solar sail. No sound, no resistance, just steady pressure from the sun nudging you gently toward the stars. As our solar sail glides silently onward, let's look back at the worlds we've passed, not at the planets themselves, but at the companions that circle them, because not all moons were born where they orbit. Galactic recycling, how stars are reborn. Everything you are, your bones, your blood, the iron in your hemoglobin, was once inside a star, not just warmed by one, made by one. And when stars die, they don't just disappear, they give back. This is the quiet cycle of galactic recycling. Stars are born from clouds of gas and dust, nebulae drifting through the arms of galaxies. Under gravity's pull, these clouds collapse, spinning tighter, heating up. Deep inside, nuclear fusion begins. Hydrogen atoms fusing into helium, releasing energy. A star is born. For millions, sometimes billions of years, it shines. But eventually, fuel runs low. The core contracts. The outer layers swell. For stars like our sun, this ends as a red giant, and then a quiet release, shedding layers into space, forming a planetary nebula. The core becomes a white dwarf, glowing faintly for eons. For massive stars, the ending is more violent. They explode in a supernova, tearing themselves apart. The explosion spreads heavy elements, oxygen, carbon, iron, even gold, into space. These elements don't vanish, they drift, and over time they become part of new clouds, new nebulae, and from these, new stars are born. But not just stars, planets, moons, people. Our solar system formed from a recycled cloud, rich with elements from long-dead stars. That's why Earth has iron, uranium, calcium, why your brain needs phosphorus, why your body carries stardust in every cell. Even now we see this cycle. Telescopes like Hubble and James Webb have captured star-forming regions like the pillars of creation, massive tendrils of dust where stars ignite inside dark cradles. And around those new stars, disks of debris, slowly forming planets. It's a story of death, but also renewal. Galaxies are not static. They are ecosystems. Stars are born. They live. They die. They give. And the cycle begins again. So tonight, as you breathe softly in the dark, know this: you are not just part of the universe. You are part of its memory, forged in the fire of ancient stars, living proof that nothing is ever truly gone. From the ashes of reborn stars, let's now look outward, not at what we've made, but at what has entered our solar system, uninvited, silent travelers from other suns. Interstellar visitors, objects that came from other stars. For most of history, we believed the solar system was a closed loop, a family of planets, moons, and asteroids, all born from the same cloud, orbiting the same sun, bound by gravity. But in 2017, something changed. A telescope in Hawaii detected a strange object passing through the inner solar system. It was moving fast, too fast to be from here, and its trajectory was hyperbolic, meaning it wasn't orbiting the sun. It was simply passing through. They named it Oumuamua, a Hawaiian word meaning scout or messenger from afar. It was unlike anything we'd ever seen. It was long and thin, maybe a cigar shape or a flat pancake, depending on how it tumbled. It had no tail like a comet, but still seemed to accelerate slightly, as if pushed by something. Some suggested gas venting. Others wondered about light pressure. A few even whispered about alien technology. But no one really knew. Oumuamua was the first confirmed interstellar object ever observed passing through our solar system. And then it was gone. Too small, too fast, too far. 2 years later, in 2019, we spotted another, a comet named Borisov, visibly different, icy, active, with a glowing tail. But again, its orbit clearly showed it came from beyond our sun. Unlike Oumuamua, Borisov behaved like a normal comet, just one born around a different star. These events changed everything. They proved that objects from other star systems do wander and sometimes enter ours. The space between stars isn't empty. It's scattered with rogue comets, stray asteroids, and forgotten fragments. And they're hard to catch. These objects are small, fast, and come from unknown directions. We only spot them by chance. A flicker in a telescope, a light curve that doesn't belong. But with new observatories like the Vera Rubin telescope, we expect to see many more in the coming years. Each one is a message in a bottle, a relic from a different solar system, a sample of chemistry from stars we've never seen. So tonight, imagine looking up and knowing that somewhere in that darkness, a visitor is drifting past, briefly, quietly, and then vanishing back into the stars. We've just watched a visitor pass us by from another sun. Now, let's turn toward the places where light seems to end, and yet sometimes explodes outward with unimaginable force. Black hole, jets, beams from the abyss. Black holes are often described as cosmic vacuum cleaners. Objects so dense, so compact, that nothing, not even light, can escape once it crosses the event horizon. But strangely, black holes are also some of the brightest objects in the universe. How can that be? It's not the black hole itself that shines. It's what happens around it. When gas, dust, and even entire stars fall toward a black hole, they don't plunge straight in. Instead, they spiral inward, forming an accretion disk, a whirling storm of matter heated to millions of degrees. Friction, magnetism, shear forces. The disk glows in X-rays and gamma rays, brighter than entire galaxies. But that's not the strangest part. From the regions just above the poles of some black holes, jets of matter are launched at nearly the speed of light. Focused, narrow beams, stretching thousands of light years across space. These are relativistic jets, powerful, focused streams of plasma. We still don't fully understand how they form. Most theories point to magnetic fields, twisted and amplified by the rotation of the black hole and its disk. These fields funnel matter into beams, shooting it out with extreme energy. Some of the biggest jets come from supermassive black holes, the kind found at the center of galaxies. One famous example is in the galaxy M87, whose black hole was the first ever imaged directly. The jet from M87 is so large, it would stretch beyond our solar system thousands of times. But smaller black holes can create jets too, even ones just a few times the mass of our sun. In fact, we've seen them in binary star systems, where a black hole feeds off a companion star. The jets don't last forever. They flicker, pulse, collapse. But while they live, they shape galaxies. They heat gas, regulate star formation, and may even sculpt entire galactic structures. So when we think of black holes, we often imagine silence, darkness, an ending. But just outside their reach, there's light, movement, fury, and somehow, from the edge of nothing, comes a signal. So, as you drift deeper into calm, picture this: a black hole spinning, matter swirling around it, and from its poles, two perfect beams racing into the void at nearly the speed of light. Silent, focused, beautiful. After the fury of black hole jets, let's now ask a quieter question, one that feels almost philosophical. How cold is space, really? And what does temperature mean when you leave everything behind? The temperature of the universe. How cold is the cosmos? Space is often described as cold, but that's not quite right. In truth, temperature in space is a complicated thing. Temperature in physics refers to the motion of particles. The faster they move, the hotter they are. In space, especially in the void between stars, there are very few particles at all. No air, no breeze, just emptiness. In that emptiness, there's nothing to bump into, nothing to transfer heat. So in most places, it's not just cold, it's almost absolute zero. The coldest possible temperature in the universe is negative 273.15 degrees Celsius, or 0 Kelvin, where atomic motion nearly stops. And the background temperature of the universe, the quiet afterglow of the Big Bang, is measured at just 2.7 Kelvin. This faint glow, called the cosmic microwave background, bathes all of space. It's not visible to our eyes, but it's everywhere. A soft radiation that tells us the universe was once hot and dense and is now cooling eternally. But here's the twist. Some parts of space aren't cold at all. The corona of the sun, its outer atmosphere, reaches temperatures of over 1,000,000 degrees Celsius, but it's so sparse it wouldn't feel hot to the touch. In fact, your skin would freeze in the shade of space, even if particles around you were incredibly hot. Because heat in space isn't about temperature alone, but how much matter is carrying that energy. And then there are cold traps, places like the permanently shadowed craters on the Moon or Mercury. These can fall below minus 250 degrees Celsius, colder than deep space itself, shielded from sunlight for billions of years. The coldest known natural place in the universe, a region of the Boomerang Nebula, measured at just 1 Kelvin, colder than the cosmic background itself, due to expanding gas that chills as it spreads. So when we say space is cold, we mean it in many ways. Cold in motion, cold in silence, cold in the sheer absence of contact. And yet, through this frozen dark, stars are born, galaxies turn, life begins. So tonight, imagine floating in that emptiness, no air, no sound, only the whisper of ancient radiation and the soft hum of a universe still cooling, second by second. From the chilled fabric of the cosmos, we move inward again to a familiar red world, but this time, not to its valleys or storms, but to two silent companions that follow it endlessly through the dark. The moons of Mars, Phobos and Deimos. Mars is a lonely planet, dry, rust-red, wind-swept, but it's not entirely alone. Two small moons orbit it, Phobos and Deimos. Their names, drawn from Greek mythology, mean fear and terror, and fittingly, they're among the strangest moons in the solar system. They are not round like our moon. They are not grand like Europa or Titan. They look more like asteroids, dark, lumpy, irregular. Phobos, the larger of the two, is only about 22 kilometers across, small enough to fit inside a city. Deimos is even smaller, around 12 kilometers. Both are potato-shaped, covered in dust and craters. Their surfaces are soft and porous. Their gravity is weak. You could leap off Phobos and never come back. They orbit close, especially Phobos, which races around Mars every 7.6 hours. So fast it rises in the west and sets in the east, twice a Martian day. But where did they come from? For decades, astronomers debated whether Phobos and Deimos were captured asteroids, relics from the early solar system, pulled in by Mars's gravity. Their size and shape seem to support that theory. But there's a problem. Captured objects usually have tilted, elongated orbits, chaotic paths. Yet Phobos and Deimos circle Mars in near-perfect equatorial orbits, as if they were born there. Some scientists now suggest a dramatic past. Maybe long ago, Mars was hit by a giant impact, throwing debris into orbit, like how Earth's moon may have formed. That debris could have coalesced into moons. If true, Phobos and Deimos might be the last survivors of a larger family of satellites, now lost. And Phobos is doomed. Because it orbits so close, Mars's gravity is dragging it downward. In 30 to 50 million years, it will either crash into Mars or break apart, forming a temporary ring around the planet. Deimos, farther out, is slowly drifting away, like Earth's moon, escaping inch by inch. So, as you lie still tonight, imagine them, two dark stones drifting around a red world, quiet, misshapen, ancient, one falling, the other fleeing, forever circling in silence and dust. After watching Mars's moons drift in silent paths, we now return to the stars, not their light, but their subtle motion, because even stars can tremble. Starquakes when stars tremble. Stars may seem eternal. From Earth, they appear fixed, steady, the same constellations, night after night. But stars are not still. They pulse, they breathe, they quake. These are starquakes, tiny oscillations on the surface of stars, not cracks or fractures, but vibrations, like the ringing of a giant celestial bell. Just like earthquakes reveal the inner structure of Earth, starquakes help us understand what lies beneath the surface of stars. This field of study is called asteroseismology, the science of stellar quakes. So how does a star quake? Deep inside every star, nuclear fusion is raging. This produces heat, which rises, churns, and flows outward in convective currents. These movements cause pressure waves. Some travel through the star, others ripple along the surface. As they do, they make the star oscillate. Not enough for the naked eye to see, but enough for telescopes to detect. Instruments like Kepler and TESS measure tiny changes in brightness, fractions of a percent, caused by these oscillations. Each frequency tells a story. Different vibrations probe different layers, from the outer shell to the deep, dense core. And from this, we can measure things once thought invisible. A star's age, its density, its internal rotation. We've learned that even the sun has starquakes, continuous subtle motions driven by its dynamic interior. These are called helioseismic oscillations, and scientists have mapped them in detail. Some stars, like red giants, show more dramatic pulsations. Their outer layers swell and contract in rhythmic cycles, glowing brighter and dimmer like a slow breath. Other stars, like Delta Scuti or Cepheid variables, pulse with regular beats, so consistent they're used to measure distances across galaxies. In rare cases, a starquake can even cause a sudden jump in brightness, like a flare, but caused not by magnetism, but by structural shifts in the star's own body. These tremors may be faint, but they connect us to the hearts of stars. So tonight, as everything around you stills, imagine a distant star trembling softly, its surface rippling, its light flickering, not from chaos, but from rhythm, the quiet breath of a sun, the music of a star. After feeling the tremble of distant suns, let's take one last quiet step, not into stars or galaxies, but into the air that surrounds alien worlds. Because atmospheres can speak, even when no one's listening. Alien atmospheres, what we've found on distant worlds. In the last few decades, we've discovered thousands of exoplanets, planets orbiting stars beyond our sun. Some are giant, hot and fast. Others small, cold and quiet. But among them, a few have something more, an atmosphere. And that changes everything. Atmospheres are more than just clouds or weather. They are chemistry. They trap heat, scatter light, and reveal what a world is made of. Sometimes they even whisper of the conditions for life. But how can we study them from light years away? The answer is timing. When an exoplanet passes in front of its star, a tiny fraction of starlight filters through the planet's atmosphere. That light gets altered. Different gases absorb different wavelengths. By analyzing the changes, scientists can detect the fingerprints of molecules. This is called transmission spectroscopy. It's how we've found water vapor, methane, carbon dioxide, sodium, even hydrogen, floating in alien skies. Some atmospheres are blistering. One planet, WASP-121b, has a stratosphere so hot it glows, with rain made of metal. Others are puffy and extended, like gas balloons drifting too close to their stars, slowly boiling away. And a few are complicated. In 2019, astronomers detected water vapor in the atmosphere of K2-18b, a super-Earth in the habitable zone. It's not Earth-like, not quite, but it's wet, cloudy, and possibly warm. We've even begun looking for biosignatures, gases like oxygen, ozone, or phosphine, that might suggest biological processes. With telescopes like James Webb, this search has accelerated. Already, it has analyzed the light from several exoplanet atmospheres measuring carbon-based compounds, haze, thermal structure. Each spectrum is a message, a decoded slice of alien weather. And yet, we've only just begun. Out of all known exoplanets, only a small fraction have atmospheres we can observe. But that number grows year by year. So as you fall asleep tonight, imagine standing on the edge of one of those worlds. The air is strange, the sky unfamiliar, but above you, a sun still shines. And in the thin, shifting mist, there is chemistry, perhaps even the breath of something alive. Rogue moons, captives of gravity. When we picture moons, we often imagine neat, natural companions, formed beside their planets, locked into orbits from the very beginning. But many moons aren't native, they're captives. Rogue objects once adrift in space, drawn in by the invisible hand of gravity and claimed. These are captured moons. Instead of forming from the same material as their host planets, these moons were once independent, perhaps asteroids, perhaps dwarf planets, wandering through the solar system until they were pulled into orbit by a larger body. It's not easy to do. Capturing a moon requires more than just gravity. An object must lose energy to stay bound, often through collisions, gas drag, or interactions with other moons. But when it happens, the result is striking. Take Triton, Neptune's largest moon. Triton orbits backward in the opposite direction of Neptune's rotation, a clear sign it wasn't born there. Scientists believe it may have once been part of a binary system, like Pluto and Charon. When it passed too close to Neptune, complex gravitational forces tore the pair apart, and Triton was caught. Its capture likely disrupted Neptune's existing moons, perhaps destroying or ejecting them. Now, Triton is slowly spiraling inward. One day, it may crash into Neptune or be torn into rings. Then, there are the irregular moons of Jupiter and Saturn, dozens of small distant satellites with tilted, elongated, and often retrograde orbits. These are classic signs of capture: chaotic, distant, and diverse. Some are just a few kilometers wide. Others are leftovers from violent impacts. All are reminders of how messy early solar history was. Even our own moon, once thought to be captured, now appears to have formed from a giant impact. But the theory of capture still lingers in the story of other worlds. In fact, capture may still be happening. Mars's moons, Phobos and Deimos, are small and misshapen, possibly asteroids caught by Mars long ago. So, when you look up at the sky, remember, not all moons belong where they are. Some were stolen, some were lured, some were simply in the wrong place at the right time. And tonight as you rest, imagine drifting beside one, a moon that once wandered freely and now circles quietly, endlessly, under a foreign sky. After following the captive moon across foreign skies, we now turn our gaze to something larger, the life of stars themselves. Because in the universe, nothing is truly wasted.